Okay, so we're back. Day 4. This is a fun day. The next 2 days are really interesting for me personally. First couple of days we were building up many basic principles, and now we're really getting into hardcore medchem, and drug metabolism is certainly important. I had used this slide before. In order for a drug to exert pharmacological action, it has to get to the site of action. That's distribution. But after it gets to the site of action, it needs to persist long enough in the body. And the body is trying to get rid of xenobiotics and drugs. So there are enzymes in the body, particularly in the liver, that are responsible for metabolizing drugs and other biochemicals that we might ingest, deliberately or accidentally. And then you also have fecal elimination and urinary elimination that get rid of these drugs. And so that's another area that fluorine and fluorination strategies are used to perturb the properties of molecules such that they eliminate differently. So today we're going to be talking about metabolism, and there are a lot of basic properties that we'll talk about again today. In this specific lecture, we're going to be talking a lot about bond strengths and electron clouds and density. We'll talk about inductive and resonance effects and stability of intermediates. These are all really basic principles, and I was trying to prime you. On Monday, I was trying to prime you for this discussion here today on day 4. Okay, so we'll use a lot of those principles. Ultimately, we're thinking about the stability of molecules and are they going to avoid metabolism. Much of the discussion today, it comes from a perspective article it's been reviewed once. It was resubmitted while I was here a couple days ago. And so there's a Chem Archive version that you can find. We posted a new Chem Archive, but it hasn't been approved yet, so it might come out in the next couple of days, but there will be an update to this hopefully sometime soon. But it is a submitted manuscript. So one thing I want to do right at the beginning, and I know we have first-year students, and we have some senior students here and faculty, but I want you to take about 2 minutes and look at these molecules. You have them on your pages there. And if you saw these, well, you see them now, what are the proposed metabolites that you would predict from these molecules? Okay, it might be tougher for some first-year students, some senior students that have had more metabolism, have more experience reading journals, might have an idea of what might happen here, okay? But take about 2 minutes and predict for me. What do you think is going to happen? We're going to see a couple of these examples throughout the talk today. These exact examples we're going to see later. There are 2 questions there. Just focus on the bold one, the first one. Okay, so you've thought about them for a bit. I'm not going to go around the room and ask for a discussion right now. We're going to see these as we go through. But I want to point out some of the substructures that would jump out to a medicinal chemist and say that could get metabolized. So we have aromatic rings. We're going to talk about aromatic rings, how those get metabolized, and then maybe how you might use fluorine to stop those processes. A variety of aliphatic substructures. You can see a benzylic position, you can see ethers, you can see amines, basic amines that have alkyl groups attached to them. More aromatic hydrocarbon grease in that naphthyl system. Okay. So there are lots of different substructures in drugs. Metabolism can occur to CH bonds, it can occur to carbon-nitrogen bonds and carbon-oxygen bonds. You can be breaking those by unique mechanisms. And we're going to talk about how those processes go. And in order to understand why fluorine works, you have to first understand a little bit about the enzymes that promote the degradation of the drugs and the mechanisms by which those enzymes function. Okay? So let's talk a little bit about those enzymes. And first, we need to think broadly about drug metabolism. And so drug metabolism can occur by a variety of enzymes. About 50% of approved therapeutics are metabolized by a family of enzymes in the liver called CYP enzymes, cytochrome P450 enzymes. That's the blue areas over here. 50% of approved drugs get metabolized by CYP metabolism. You have some non-CYP metabolism that occurs. We'll talk a little bit about some of that, and then sometimes we just don't quite know. But it works, and it's safe, and so we can still get approval there, even if we don't understand every single thing about the drug's metabolism. We do a lot better now than we used to. Nonetheless, there are still some unknowns about how some of these drugs are getting degraded. Within this 50% grouping of CYP-mediated drug metabolism, there are individual isoforms of P450s responsible for the metabolism. In general, CYP3A4 and 2D6 are responsible for over 50% of the P450 metabolism. So those are huge players, but there are also other CYP isoforms, 2C8, 2C9, 2C19, 1A2. There are many different isoforms responsible. And then for some of the non-CYP mediated metabolism, you have glucuronidation, sulfation, you have the cleavage of esters by carboxyesterases, monoamine oxidases are down there. Okay, so there are many types of processes that can happen. All of these processes here are these non-CYP processes. The glucuronidation is certainly a big player there. And we'll talk a little bit about glucuronidation and sulfation later on. Okay? So in general, we think about two major processes that occur, two classes of processes that occur in drug metabolism. Historically, these are called phase 1 and phase 2. There are some reasons for which we don't want to be using phase 1, phase 2 as much anymore, and instead we use oxidation phase and conjugation phase. But when you look at the literature, you might see a lot of phase 1, phase 2. Historically, oxidation is phase 1, phase 2 would be conjugation. The oxidation phase generally involves the conversion of some type of carbon-hydrogen bond or maybe an ethereal type bond, an aromatic ring, to a substructure that has a hydroxyl group or some other reactive intermediate. That increases water solubility, and it also presents a moiety that can be exploited in the conjugation phase to further promote elimination. In the conjugation phase, the body will attach some type of moiety, a glucuronide that's here, the glucuronide transferases are a class of enzymes that puts on a substructure looking like that. You can have glutathionylation reactions that react with electrophiles that will put on a moiety. These moieties are typically exploited by transport enzymes for exporting cargo out of the system. Okay. So in the liver, you have enzymes that are going to oxidize your molecule and then attach some type of moiety that then pushes the molecule out of the body. Okay. So it's, again, Some people call it a two-phase system, but it's an oxidation and a conjugation series of steps that promote this reaction, okay? So that's the big picture of what's going on in drug elimination. Since 50% of drugs are metabolized through this oxidation by P450s, maybe we can talk a little bit more about that and remind everybody of some basic enzymology. So this would be the Michaelis-Menten model for enzyme kinetics. Okay, so I think it's probably taught sometime in year one. Okay. So when we think about a drug substance getting metabolized by the P450, we need to break that down into individual steps. In order for that drug to get metabolized, it needs to be recognized by the P450, and it'll go to the active site of the enzyme, and there's an equilibrium associated with this process. You have a rate forward, a dissociation rate going backwards, and those, when you have the ratio of them, we have a term Ka, that's the dissociation constant. After the drug binds the active site, then you have a catalytic process that's going to generate the metabolite. Okay, and so there are many mathematical treatments. Michaelis-Menten is one popular one that's used. And so when we see the discussions of drug metabolism in the literature, most of the discussion focuses on what's happening in this catalytic step, the oxidation step itself. There's very little literature discussing how the drug association occurs. But you can make substitutions to the drug such that it no longer binds well to the P450s. It's under-discussed, and that's kind of the point of my perspective, is we need to be paying more attention to the association, because we know fluorine can perturb the association of molecules, and we study that in a little bit more depth tomorrow. So, the metabolite, after it gets oxidized, can then react with subsequent enzymes and or glutathione that make the conjugates that ultimately get eliminated. Okay. And the argument here is that, yes, fluorination can definitely perturb K-cat. We also need to be thinking about how fluorination might perturb the association or the recognition. Okay. And there's very, very, very little discussion and very little data for this process here, and I think there's a gap for people studying in that space. So we're going to talk a little bit more in depth about the oxidation phase and those P450s. For those individuals that aren't aware of the P450 system, I can provide just a little bit of a background here. So P450 enzymes, it's a class of enzymes for which there are many isoforms. They are localized in the endoplasmic reticulum. They have a protein structure with a tail, lipophilic tail, that embeds and forces that enzyme to stay in the membrane. So when a greasy drug, a lipophilic drug gets metabolized, that greasy drug will exist in the membrane. Like a lot of them are lipophilic. So they're okay being in the membrane. They'll get into the water, but they'll go back in the membrane, right? We were talking about the transition back and forth across membranes. So some of the greasier drugs will be sitting in the membrane, and when they're in the membrane of in the ER, the substrates can kind of get uptaken into the active site of the P450 where they're metabolized, and then ultimately they get released as the metabolite after metabolism. So it really is the greasiness of the drug in many cases that helps get in here to start. Okay? So you can kind of see that again over here in this slide. You have the enzyme. It gets really attached through a series of amino acids with greasy moieties presented there. So you have a hydrophilic area that attaches the P450 to the membrane, and then a more water-soluble side over here. In the active site of the P450, you have a heme. Okay, and the heme structure is kind of embedded there. That heme has an iron in the middle of it, and that iron is going to be the catalytic species that reacts with oxygen, gets activated, and does all the key bioinorganic transformations that we're going to talk about. Okay? So that heme does require an NADPH reductase to help the cycle, promote the cycle and regenerate the active species. That NADPH reductase requires NAD, right? So you also have a co-cycle going on in the background. I'm not going to talk about it in depth, but you do need to be thinking about regenerating the active species using another enzyme. So there are many isoforms, and the main isoforms for drug metabolism are shown here. You can see the representative contributions to drug metabolism here out of a series of about 800, 900 drugs that were established. There's a huge variance in the active sites of these enzymes. Some of them are pretty small and linear, some of them are a little bit more round and bigger in space. Some have like little L-shaped bends in the active site, so they'd recognize molecules with different shapes. Some of them are more hydrophobic, and so they love greasy molecules. Some of them will have charged anionic residues right above the heme, so they attract cationic amines. When I'm talking about cationic amines, we've already been talking about modulating amine pKa with fluorine. So I'm trying to give you a hint about what we might be seeing a little bit further downstream. So that's in the substrate binding residues. Again, some of them are more cationic, some of them are anionic, some of them are just really greasy and recognize grease. And the representative substrates, you might recognize some of the names of some of those drugs. We never know in advance when we build a drug, like which P450 is going to be responsible. And sometimes when you optimize to try to avoid metabolism by one P450, maybe another one kicks in that you didn't expect. And so in order to do drug discovery properly, when we measure the metabolism in vitro, we'll use pooled microsomes. Pooled microsomes are like the ER. You separate the ER from the rest of the cell. That ER has the P450s in them, and then you kind of have a time course study where you subject drug to the microsome. It has the P450s in it, but it has a bunch of P450s. It doesn't have one isoform. It usually has all the isoforms there. So it's tough to study which isoform is responsible, and it takes a lot of follow-up studies to figure out which one is responsible for metabolizing your drug. Okay. So the catalytic cycle is shown here. In this case, we're using a generic organic substrate that really doesn't have a structure. But this overall process that occurs at the metal, at the heme, occurs regardless of the substrate and regardless of what mechanism is going on the organic molecule later on. So we're going to look at 3 different mechanisms later on in terms of what's going on the organic molecule, but all of them have this type of cycle for the heme. So the heme is going to have a resting state in which it's hydrated, so there's a water bound to the heme. The substrate can move into the active site of the enzyme, and water gets displaced in this process. After this, there's a reduction of the iron, and now it's in a prime oxidation state to react with oxygen. The oxygen itself, upon binding, has a 1 electron transfer, so you get back to a higher oxidation state iron. Again, another reduction occurs, and you can see the reduction here, and now we have an active species. Upon protonation, we get to a peroxide. Here's our active species. This species is what we call compound 1 in the literature. This is the key player. This is the high oxidation state species that reacts with your organic molecule. So this one right here, 16. Okay. Through a variety of processes, this iron oxo will then oxidize your molecule. There are 3 mechanisms that we'll kind of look at: arene oxidation, aliphatic oxidation, and then dealkylation reactions. We have an NC or an OC bond that gets cleaved. Okay? So there are multiple different things that can happen here, but all of them will oxidize your substrate. Eventually, replacement of the substrate, oxidized substrate with water, gets you back to the resting state. Okay? So the details of that are, in my mind, important to know the big picture of what's going on, but more critically for metabolism, you want to have a fantastic idea of what's going on there, and that's where we're going to spend a bit more time. So we're going to start with arene epoxidation. You find aromatic rings all over drugs, and fluorine is well known to help modulate the properties there. So the mechanism of what's going on in this case is shown here. In general, this is the active species, that compound 1 that I had mentioned before. I'm going to be using this term. But remember, it's that iron with a double bond to oxygen there. And then the heme and the whole enzyme is there. But as an organic chemist, an organic metallic chemist, I can, pretend like the rest of the enzyme isn't there and think about the metal and the redox chemistry going on at the metal as being like a just really simple iron oxo species. Okay, so we can simplify for purposes of the discussion here. So the arene itself undergoes electrophilic attack. So the iron oxo is electrophilic. You can see the charge on that species. The pi electrons will attack, generate this type of cationic intermediate here, and then there are two pathways that can occur after this step. In one pathway that's commonly used to rationalize the metabolism, you can reform a second bond between the oxygen and the cation, and that gives you an epoxide or an arene oxide, and that arene oxide can undergo an NIH shift. That NIH shift involves the movement of electrons from one of the CO bonds to the other to make a double bond. You can't have 5 bonds on carbon, so you'll have a hydride shift. H minus will shift back over to the other position. That generates a ketone type intermediate, which spontaneously, rapidly tautomerizes to a phenol. So we see the phenol metabolite. It looks like we've replaced a CH with a CO, but the mechanism is not a CH activation, CH insertion. The mechanism requires different steps. In a second mechanism that also occurs for some substrates, you can have an NIH shift directly from this cationic intermediate. So from the iron-oxygen bond, if you think about those electrons as forming a CO double bond, and then the hydride shift quenching the carbocation, you get to the same intermediate that ultimately tautomerizes. Okay. So those are two different mechanisms that get you to the same product, and there's evidence in the literature for some substrates you go through one process, for other substrates you go through the other process. A key point to remember in this mechanism is that the pi system of the arene is nucleophilic. The pi system attacks the electrophilic iron oxo. It's not the CH bond. It's not a CH bond insertion. Okay. And as such, we should be thinking critically about the pi density and substituents on the ring that increase pi density might accelerate this process. Substituents on the ring that decrease pi density might decrease the rate of this process. But CH bond strength is not the key driver here. You don't do anything with CH bonds until you get to later steps in the process. Okay? So keep that in mind. Then we'll start to think about how different substituents, including fluorinated substituents, perturb pi density, and then how does that relate to drug metabolism. So these are some calculations that my group did, still unpublished, but submitted for publication. Is that a military plane? That's a different engine, different type of engine, sounds like. Okay, so as a benchmark for these, we're going to be using benzene as a benchmark, and we have a couple of other comparators built into here. For benzene, we have HOMO energies, and then you can see the diagram here. Red means there's more electron density. The greens and the blues mean less and less, less electron density. So benzene, you have that pi system that's above and below the ring. You see a nice red character there. If we go over to chlorobenzene and fluorobenzene, you see slight perturbations there, maybe not quite as pi-rich. The HOMO energies here actually get slightly less, and so that's kind of important. You get higher energy there, positive trend, so you actually accelerate metabolism because the HOMO energy is a little bit higher there. It's more nucleophilic, higher HOMO energy. Remember, these are negative values, right? So you have to kind of recalibrate yourself. These are negative values. Okay, so when you get to difluorination, here we have 1,2-difluorobenzene, 1,3-difluorobenzene. We see the HOMO energies still being pretty close not a great perturbation in the HOMO energies. So those catalytic processes for these simple model systems are anticipated to be very similar. When you start to get down to trifluorinated substructures, 1,2,3, 1,2,4, 1,3,5 trifluorobenzene, that's where you start to see a little bit more of a notable decrease in the HOMO values. You see more of a green color in there. And now we're thinking that maybe we're decreasing electron density sufficiently to perturb metabolism. So don't always expect a huge benefit from monofluorination. Sometimes it works, many times it won't. Difluorination, you had a little bit better chance. If you're really trying to drive that HOMO energy down, you need 3 fluorines in there to have a significant likelihood of success. Okay. So we're going to look at another series of compounds. We're going to start with toluene and look at CF3 derivatives. So you can see the toluene energy is there relative to benzene, 0.34, but that 6.14 is what you want to keep in mind. You lower the HOMO energy pretty drastically when you put 1 fluoro, 2 fluoro, 3 fluoros on that methyl group. So now we have trifluoromethylbenzene, right? Fluoromethyl, difluoromethyl, trifluoromethylbenzene. Our HOMO energy value has gone down pretty substantially. You can still see a lot of the yellow and the green character there. If you have bis trifluoromethyl substructures, that HOMO energy drives down quite a bit more. So now we think about a less and less and less nucleophilic pi system. There's another one, and then there's another 1,4 bis trifluoromethylbenzene. And then just for comparison with some other functional groups that you might see in drug discovery, we've done some calculations. You have anisole that increases the HOMO there. Difluoromethoxybenzene, trifluoromethoxybenzene, those are how you would take an anisole and reduce electron density again, lower that HOMO. And so this is another nice series that might be valuable to think about for your own campaigns. Nitrobenzene, powerful electron withdrawing group, lowers the HOMO to minus 0.76. Benzonitrile, another electron withdrawing group you'll see in a lot of drugs. We're going to talk about this substructure in one of the key examples when we move forward. Anilines and phenols are considered to be really redox active. They're not always the most stable substructures in drug discovery. And those are easy to oxidize. Pyridines, incorporated into many therapeutics, lower the HOMO energy. They're less nucleophilic than benzene. The calculations support that, and we are going to use this one in some of the structures also, in some of the discussions. And then indole, electron-rich heterocycles, raise it back up. Okay, so this is intended just to get you thinking about the pi density more than anything. The quantitative values I don't expect you to be applying here right now in class, but they are documented in there. So let's go ahead and start talking about examples now. I've kind of laid the basis. These 2 examples, the one on the left is the one we're about to cover, and that's one of the ones I asked you to look at right at the beginning of class. Okay, so let's look at that one. That's a precursor to a compound that made it into phase 3 clinical trials and failed because it had some other adverse effects that weren't desirable. So in this series, the parent compound, and the one you looked at before, is a compound for which this was a hydrogen atom, and over here you just had a phenyl ether. And this compound it underwent metabolism. Metabolism occurred in microsomes, and the working mechanism and the speculated mechanism is that it underwent arene epoxidation, and then the arene oxide reacted with glutathione to make adducts that look like this. And they could detect those glutathione adducts. And then a second thing that they could detect, when you have these arene oxides, they can also react with nucleophilic residues on the microsomes. And so you can detect adducts that have the drug bound to the microsome and quantify those. Okay, so that's the covalent binding to liver microsomes that they're talking about right here. So that's what's going on with the data. The parent compound itself is a 2 nanomolar inhibitor, antagonist of a cannabinoid receptor. The Formation of both the glutathione adducts and the human liver microsome adducts was detected in high quantities. In order to reduce metabolism, the group needed to have less nucleophilic pi systems. They focused on the electron-rich phenolic ring. Phenol, this one's a phenol. This is an electron-rich ring. This one is neutral when it's just the phenol, right? So this one's likely going to be more active. And in the next series of entries that I'm presenting here, there are many others, but I'm just presenting, the team tried a couple of different substitutions. The 3,5-difluoro was a potent compound, maybe a slight reduction in the covalent adducts, but not enough to push the program forward. The pyridyl substitution that I had mentioned a slide ago was used, and that further reduced the covalent adducts that were being observed in this case. That wasn't enough. They need to keep reducing electron density. You're still seeing some of those adducts form, so let's continue to introduce more and more and more electron withdrawing groups. So the chloro and the CF3, both sigma withdrawing groups, inductive withdrawing groups were used here. You can see the 5-chloro, the 5-trifluoromethyl, still potent compounds, fewer and fewer of those adducts being formed. At this point, the metabolism of the aryl ether system was negated. And in drug metabolism, if you completely block one moiety, it's common that an alternate moiety in the system gets metabolized by a different P450 enzyme. And that's where they started to observe oxidation of the neutral ring over here. Now this is the most electron-rich system. After they block this one, metabolism starts occurring over here, so now we have to solve that problem. In order to solve that problem, same general strategy, let's make a series of analogs that have less and less electron density over here on this system. Ultimately, the combination of the 2-pyridyl 5-trifluoromethyl, aryl ether over here, with an electron withdrawing nitrile, suppressed formation of the covalent adducts and ultimately delivered the clinical candidate that made it to phase 3. Okay. So a lot going on here, but it's a great story where on 2 different ring systems, they're having to reduce electron density ultimately to reduce the metabolism. Okay. So in a second example that we'll talk about, this is the development of gefitinib, an EGFR inhibitor that is approved for cancers. An early lead compound has this substructure here, the 4-amino-quinazoline substructure with 2 ethers, screams out EGFR, like this ring system over here. You see enough of these drugs that's common. It's a pharmacophore in many of them. The early fragment-sized compound had this aniline with a methyl group on it, and that was determined to undergo metabolism. Of course, a lot of these compounds go through metabolism. That's why it's a metabolism lecture, right? So it underwent metabolism to make 2 different, metabolized predominantly. You can see aromatic hydroxylation occurring over here, benzylic hydroxylation occurring over there. We'll talk about benzylic hydroxylation in a different part of the lecture. So in order to further develop this compound, you want to think about removing electron density from the aniline ring system, because that's the electron-rich system. Many analogs were made. Another important derivative in this series was the chloro-fluoro derivative that extended the half-life of the compound from 1 hour to 3 compounds in vivo. This is in vivo PK data here. And then with the extended half-life, further medchem optimization, changing the substituents here, delivered the clinical candidate and ultimately approved compound. I'll say there's a typo here. That should be OME that I'm just seeing right now. Okay, so that should be a methyl ether. So that's the drug. Key point here is that we're removing electron density from this system that has an aniline donating in and a methyl group donating in. And we did some calculations to estimate what the homos of those fragments might look like, what type of pi density is in those systems, and the starting point, the toluidine right here is shown there. You can see how red that is from the donation of both moieties. You can attenuate the pi density, reduce the pi density, attenuate the metabolism with the chlorofluoro that both pull electron density out through sigma withdrawing effects. Okay. So that's a story there. Main point, when you're thinking about the metabolism of arrow rings, think about the pi density. You can do these types of calculations pretty quick, or just look at linear free energy relationship parameters and you can get a feel for electron-rich and deficient systems there. Your intuition and arrow pushing is also fantastic as a first attempt at any of this. So let's talk about aliphatic. Oh, maybe I should pause there and just see if there's any questions first. Any students back? More senior students in front? Super senior students all the way in front?
Yeah, I have one question. This CYP-mediated metabolism.
This what metabolism?
CYP-mediated metabolism. So in one of the slides, this slide, there was a like metabolism happening, like oxidation happening in one ring, and which was the total ring, and then it was blocked, and then it was happening at other ring. So how CYP is actually accommodating, because that is again a receptor and ligand kind of interaction. So how come so CYP has a like very flexible kind of thing where it can accommodate?
Yeah, some CYPs are more flexible than others. And remember, there's a family of enzymes. It's not one enzyme, right? So some of them are going to recognize a lot of just grease. Some of them will be looking for a basic amine or a methyl ether, just because they have active sites that have, amino acids dangling out right above the iron that recognize certain moieties. Okay. So, it's really tough to solve it when you just think about one enzyme alone. You kind of look for trends of things that can happen in general to a drug, and then how do you stop that regardless of which P450 is responsible? Yeah, it's really tough. Okay, so we have this example here. We're going to move on to aliphatic oxidation, and this is the sub-story that you're going to want to pay attention to because of the other discussions with the aliphatic tail sticking off a heterocycle. Okay, so this is going to be directly relevant. So I'll find a good stopping point in about 20 minutes for the transition. So in this type of process, there's a different mechanism. We're talking about aliphatic CH bonds. Here we have an aliphatic CH bond. The reaction that occurs is actually an H atom abstraction, HAT. So the iron oxo will rip off H dot and reveal a radical. And then through a radical rebound process, the hydroxyl group, this first step here, when this rips off H dot, it makes this iron hydroxyl. And through a radical rebound process, we'll have one electron come from the hydroxyl, make a bond with this single electron there, and that's how we get the alcohol. Different process. This one does involve direct cleavage of the CH bond in the rate limiting step. The other one didn't. The other one had that pi system reacting. This one does involve a reaction of the CH bond. So different mechanism, different rules. We can use fluorine and fluorinated substituents to replace a CH bond with a CF bond. The CF bond, it's not going to cleave by a P450. Okay, there are two reasons. One that's cited over and over and over in the literature, and I don't think it's the better reason, but let's go ahead and look at it. It's true. The difference in CH versus CF bonds is different, so you get about a 9 kcal per mole increase in energy for a CF bond relative to a CH. Okay, that's fine, that's fair, that's true, that's good. The CH bond is certainly stronger, sorry, the CF bond is certainly stronger than the CH bond. But if you do a deeper just analysis and think about what's going on at the metal, not just looking at the ground state of the starting material, you actually get ridiculous intermediates that would form if you try to abstract the F atom using an iron oxo. So if you try to replicate this initial step with a CF bond, you would make a radical, sure, that's fine, but look at that intermediate there, OF, pretty weak bond, right? Oxygen, fluorine, both electronegative. that's not a stable species. That might actually be explosive, and we don't want cells exploding, right? So, and we did a quick energy analysis of this. So this is just a little cartoon here that shows the process if you abstract a CH bond, that's down here, and then the one that abstracts an F bond, a fluorine atom, would be shown here. There's actually a 55 kcal per mole energy difference here, so I know why while people like looking at that 9 kcal per mole difference and say, yeah, that's why it doesn't happen, I think you might also consider the energies here. And the OF versus the OH bond strength are pretty drastically different. And maybe that's a reason too. You don't have an iron oxo, the oxygen presenting towards a fluorine atom, that's going to be disfavored in the transition state that precedes this step. So that's a bad interaction right there. So just a different analysis of the same phenomenon. So that's if you replace the CH that's metabolized by a CF, but we should also be thinking about other hydrogen atoms in the direct vicinity. Okay, so if we have a methyl group and we replace one of those methyl groups, one of the CH bonds with a CF bond, how is that going to perturb the metabolism of the substructure? This is a series of model substrates. We'll look at it over a series of animations here. Your slides are just the slides that are all black, but hopefully my coloring helps walk through a lot of data more effectively. So, in the first example here, we're going to look at fluoromethane and methane. You can see fluorination actually decreases the BDE. So we put a fluorine atom in there and we make a weaker CH bond that'd be more easy to cleave by the P450. Okay, so we actually see a decrease in energy there. That's not exactly what we were looking for, but let's think about the electronic structure of the radical, and is that radical more or less stable? So when we abstract H dot from fluoromethane, we would get to the CF2H that has a single electron on carbon. Fluorine still has a lone pair of electrons, and we can get orbital mixing. In that orbital mixing diagram, we make a pi bond that involves one electron from the carbon with one electron from the fluorine pairing. The other unpaired electron from fluorine goes into the pi star, but we have two electrons going down, one up. It's ultimately a stabilizing substitution. Okay, that's why you see the weaker BDE. It's easier, it's more facile to abstract this hydrogen atom, alpha, to a fluorine atom. You have monofluorination. Now that contrasts what we would normally think about, and that we normally think about the sigma withdrawing effect. And the sigma withdrawing effect suggests that the BDE strength should be higher. So we have competing effects here. We have a hyperconjugative effect that's stabilizing. We have the electron withdrawing nature of the fluorine destabilizing that intermediate. With one fluorine atom, with two fluorine atoms, the hyperconjugative effect wins. But when we put on the second fluorine atom, so here we have CF2H, we get a little bit stronger relative to the monofluoro, but still ultimately a weaker CH bond than the methyl itself. When we put on the third fluorine atom, that's where we start to see the inductive effect outcompeting the hyperconjugative effect, and so that's where we actually see an increase in the bond association energy. Okay, so you have these competing effects that we need to think about over here. And again, these are some of the effects we were talking about in day one. As I said, they're going to become relevant as we move forward. So that is all alpha fluorination. That's all if the CH bond that you're abstracting is directly attached to a fluorine atom. But we can also fluorinate vicinally. We can keep moving the fluorine out one position, another position. So let's ask the question about what happens there in those systems. And I'll say that this system here, this is still alpha fluorination. So you see the same trend we just saw in the previous slide. We are substituting alpha with one fluorine or two fluorine atoms, and again, they're weakening the BDE. Okay, so now let's go to the system that I was talking about. If you fluorinate vicinally or beta fluorination, And in this case, everything is going to destabilize the radical. Okay. So let's look at this comparison. Here we have ethane relative to fluoroethane, difluoroethane, and trifluoroethane, but we're thinking about abstracting the CH bond that is not connected to the CFs. The benchmark number that you should have in mind for comparison is 100 kcal per mole here. We've reset our 0 point right there for the rest of these calculations. The introduction of one fluorine atom increases the bond dissociation energy. Second fluorine atom increased. Third fluorine atom, CF3, also increases. And so in this case, we're just thinking about the sigma inductive effect. You have a radical, it's electron deficient, not perfectly happy. The presence of fluorine atoms removes electron density or pulls electron density away from a species that is already electron deficient. And that's not a favorable interaction there. Okay. That's where you see the increase in bond dissociation energies if you fluorinate beta. So the situation is a little bit tricky. If you have alpha fluorination, like the ones we discussed here, over here you have no hyperconjugative effects. You're only thinking about the inductive effect. Then we see the increase in bond dissociation energies. So this strategy can be used in many different ways and has been used in many different ways. Fluorination of aliphatic systems can block metabolism or at least perturb metabolism. This is a steroid. You can see the ABCD ring system. This is a fungal species that can be used to estimate metabolism. Fungi are eukaryotic, so they have P450 systems that are pseudo-similar to mammalian systems. Okay, they're not prokaryotic, they're eukaryotic fungi. And so this is a model that's used occasionally. It's a slow model. It takes a while for these to go. Nonetheless, you can get some studies done with these types of models. So with this fungal species, they'll metabolize the steroid. They'll put hydroxyl groups on the C and the D rings there. If we want to block metabolism here of the C ring, you can put fluorinated substituents there, and that effectively blocks metabolism at this position. Now, as we saw in the tranabant example, that cannabinoid example, you block one position, maybe a secondary position that you didn't expect pops up and starts being problematic, so that's what happens in this case. When you block this position, now you start getting a new hydroxylation at the B ring occurring. Okay, so that's important to think about. Another important lesson or thought, we talked about fluorination of the site that you're trying to block, or vicinal fluorination. So if we fluorinate one position over, we can still destabilize the radical intermediate. And that's what's going on down here in this example. Okay. The species tends to hydroxylate this position right here. But we can block that position by putting fluorine adjacent. We shut off metabolism at that site, that whole ring. Don't see any metabolism there. Okay. Now you still have the primary site that gets metabolized, and the metabolism does shift over here, so you still get B ring hydroxylation. But we have effectively, for teaching purposes, we have effectively blocked metabolism of this ring by introducing fluorine at the adjacent site to the one that gets hydroxylated. Okay. So teaching point there. Finally, we can introduce fluorine to other positions. This one isn't very good necessarily for teaching purposes, but if you put fluorine down over here, you still get the initial hydroxylations that you would get anyway. So it's just a nice benchmark, a nice comparator to have to include here. Okay. So hopefully you saw that the strategy in action has been used in more complex settings. So this is an FDA-approved drug development sub-story shown here. So this is a NS3A inhibitor, an antiviral, anti-hepatitis C drug. The structure is crazy. I mean, that thing's a monster, right? And there's probably 6 or 7 drugs in this class that have similar structures to this approved now. In this lead series, reasonably optimized series, you have a vinyl group here. You can have this heterobenzylic ring system. Both of them underwent metabolism. So the aliphatic system was metabolized here at the benzylic position. Benzylic positions are notorious for getting metabolized because when you make the initial radical, it's benzylic, it's stable, because the resonance structures that you can draw are where the radical distributes into the aryl ring. So the benzylic positions are extremely susceptible to metabolism. The second process that occurred was over here on the vinyl group, and that made an arene oxide the way you would see in the first step of this made an epoxide similar to the arene oxide you saw in the aromatic case, right? In the aromatic reaction you studied, they made an epoxide. It was on an aryl ring. This is just a vinyl group. It's CYP3A4 that did that. Now, this is an electrophile, so it can react with nucleophilic cofactors, and glutathione opens this up, and then this was detected, the glutathione adduct. So we have to solve those two problems, and here's a series of examples, series of compounds that were prepared in order to further progress the project, improve potency, and also improve the metabolic properties. So I have this other substructure over here in which we're looking at R1, R2, R3, just to keep people calibrated with the positions I'm trying to focus on. I put that over there. So you could optimize some of the other aliphatic groups here, R3 and R2. You can see those. You can have H, you can have methyl, methyl ethyl. They're small, so the pockets here, you don't want to grow them too big. Nonetheless, the metabolism was not occurring at those sites, so we kind of let them be, let the SAR that drives the potency really control the decisions here. The smaller substituents seem to work well. The clearance is important here. That was a weird noise. Okay. So the metabolism is shown here. These are reasonably high numbers. We want to get these numbers down to those that you see down here. Okay. In order to address the metabolic issue over here at this vinyl position, that would be R1, there were some attempts to change the pi bond to just an aliphatic system there. You're still seeing some metabolism at that site. That was still occurring. So in order to block the metabolism at that site, a fluorination strategy was employed. So here you can see a series of fluoromethyl and fluoroethyl derivatives, reasonably potent compounds, some of them, and a decrease in the clearance in hepatocytes. So that was a good success story. You have not yet addressed the metabolism occurring over here at the benzylic position, but the fluoroalkyl substitutions here did benefit the metabolic, or avoid the metabolism down here on what was a vinyl group. Ultimately, a combination of fluorination strategies was used in this case. So you still have the CF2 group over here, the monofluoro and difluorinated substructures were introduced here, and you can see a decrease of the metabolism and shutting that down pretty significantly with the difluoro. Really nice potent compound. This ultimately became an approved drug. So fluorination at different sites became relevant here. In one case, we're dealing with the benzylic fluorination. In the other case, this was an interesting group. You don't see many vinyl groups in drugs, predominantly because they can get oxidized, make an arene oxide. And this was a nice strategy used here to stop that. Okay. So I'll pause after a couple of stories. How are we doing? Good? Okay, I'm going to work through another series. I'm going to introduce a couple of slides, and then there are several slides of data that you can read through on your own. But I'm going to talk through the general principles and walk through a couple of the slides, and then the rest are just like an attachment for you to look at on your own. So I want to introduce a concept called vicinal difluorination. We've seen the CF2 group all the time, right? You see it in a lot of different drug discovery campaigns. It turns out that vicinal difluorination can introduce distinct properties relative to geminal difluorination. The reason why is shown here. When you think about the dipole introduced by each fluorine atom, the overall perturbation and properties will be the result of the sum of those vectors. Okay, so if the net vector is greater, you're going to see a bigger perturbation and properties. When you have geminal difluorination, you have two vectors that are at 90 degrees from each, tetrahedral, yeah, from each other. And so the sum of the vectors, part of them cancel each other out, so the net sum is smaller than if you have vicinal difluorination. If you have vicinal difluorination, the sum of the vectors is going to be greater there. And that further modulates properties. You can see the summary is right here. So when you think about the changes in lipophilicity, geminal difluorination typically makes things greasier than vicinal difluorination. So if you're trying to drive water solubility, you can do it better with this type of substitution. And so that's what's shown here. Vicinal difluorination is shown there. So log P and solubility in water, they work against each other. In terms of metabolic stability, the vicinal difluoro seems to be more stable in a series of model systems also. So again, pretty important for some campaigns that might have long aliphatic systems attached to a ring. And so I can show you a little bit of data to support that.
Then the vicinal one, the log P is actually okay. That means the geminal. This one is more hydrophobic in nature.
This one will be more lipophilic
so this will
than
bind
this.
Bind also in the enzyme maybe in a better fashion. So that is the reason it will get it. Yeah, that's right.
This is a little bit greasier than that is.
So that
Yeah.
will bind also to the enzymes in a better fashion.
For P450s that just look for grease,
Yes.
this is more likely to engage those ones than this substitution pattern. Okay. So here's a series of compounds. You can see the changes in lipophilicity. Maybe just to benchmark everybody, here's the aliphatic system. If you put like a fluorine atom or CF2 group, again, you drive water solubility a little bit because we talked about this on day one. Day two. No, yesterday. Yesterday was solubility, right? So slide one yesterday. We talked about this, how if you start fluorinating aliphatic, you increase water solubility. Okay? And you see that here. The log P, as you put a couple of fluorine atoms, gets more water soluble. Okay? Decrease in log P. The key comparator for this discussion, there are a couple of them, maybe this compound versus this one, and this one versus this one. You can see these ones are less lipophilic. This one, the vicinal difluorination, and these ones over here. And you can see it in some other systems too. I have quite a bit of data. The second important correlation here is to show the correlation between lipophilicity and metabolism. And you can see the correlation. We try to lay these out. So you can see the correlation that goes up and right. As things are greasier, they tend to get metabolized more quickly. As things become more water soluble, the metabolism does shut off a bit. Okay. And the same is true in other systems. These are systems for which you had an ether linkage between your heterocycle and the aliphatic system. Okay, these are systems that are similar. You just don't have the ether. So this is just the alkyl group coming off the heterocycle. And again, this is where we start thinking about, your substructures that you were thinking about there. Okay, so you can, with this vicinal difluorination, you can decrease lipophilicity overall. And you can pattern these fluorine atoms in a variety of different manners. And you can think about the stereochemistry. Maybe you can influence potency or selectivity for your target by having stereo centers over here on your molecule. Maybe you don't want to worry about that, but it's up to you. But in general, the vicinal difluorination is a greasier substitution. The CF3 is a greasier substitution than some of these other ones that are vicinally substituted. And so again, more data. There's more data in these. This is water solubility here. So now we're looking at log P versus water solubility. You see the inverse correlation, so the less lipophilic ones. But look at that. Look how much. Look how soluble that is. That's crazy, isn't it? Yeah. Okay. And then the clearance there. So let's look at a couple of examples right before the break. This is that fungal model again. We saw the patterning of these cyclohexanes in a previous lecture. And so here they're coming up again in the metabolism. In an example here, we see metabolism of the aliphatic system at several different positions. Around the aliphatic ring, you see some of the benzylic position that gets metabolized too. 100% conversion. If we put another fluorine atom, we decrease the metabolism, we still see benzylic fluorination there. You can see the decrease in log P, and if we put another fluorine atom in there, we're, again, a little bit less lipophilic, a little bit more stable, less metabolism occurring in this system. So you can use multiple fluorine substitutions to drive metabolism. So, yeah. I'm going to pause. That's the end of this subsection. Any questions before we break real quick? People ready for tea? Okay, so we'll get some tea and we're going to come back. What time do you want to start the next one? It's 11:17? Yeah.
Yeah, we'll take a 15 minutes break. 15 minutes break, and then we'll either dive.
Okay, 15 minutes? Cool.
Hello, is it okay? Yeah. So welcome back to post T session of this day 4 of this GIAN course. So as we discuss many aspects of fluorine chemistry, one important aspect is also characterization of compounds. And for that, we are going to discuss more about fluorine 19 NMR. So for that, we have today Srinivas from Jewel India. He's an application expert, and he is located at Bangalore. And right now, you all know that we have two Jewel machines. We also have Sandeep and Dr. Archana, who are the experts who operates our NMR. So what I asked Srinivas to give a brief overview about NMR, because I just want to mention, Srinivas, that we have there's some problem. We have first year MPharm students, mostly who just started learning NMR. So so try to see little briefly if you can give a brief info about basics. I think they have completed 4 to 5 lectures so far in NMR. Then based on whatever you cover, then I will also cover some basic aspects in the evening today or sometime tomorrow. So Srinivas has a very good, he's an organic chemist, so he understands small molecules, and it is very good that an organic chemist, and then after his masters from after his masters he joins IISc Bangalore, and he was taking care of the NMR facility over there. After working there for 3 years, then he has moved to Jewel. Okay, and then so with this background, I will also request Srinivas to give a brief background about himself, because about his trajectory, so that students can have an idea that maybe that could be another kind of a possible job prospects. So with this, I request Srinivas to give a talk on fluorine NMR.
Good morning, all. And first of all, thanks, sir, for calling us for this involved into the intense workshops, mainly on the synthetic backgrounds. And again, of course, we are the manufacturer of analytical instrument. It's a good opportunity for us to be interact with the young mind and the experts of synthetic groups, and understanding your problem and what the spectroscopy techniques can give us solutions. And some of the techniques may not be known by the users, or some may be using very routine experiments like simple like proton, carbon experiment, or maybe a simple 1D experiment based. There are maybe a advanced experiment, and there are something like interesting experiment which is unrevealed by the chemist. So the reason is, being an NMR spectroscopist, if we talk about that, we have 1,000 pulse programs available in the library. But it is not untouched. It's all are one by one added and are revised based on the problems. So, and today is, as for the focus, we are talking about only fluorine nuclei and in NMR spectroscopy. Okay. Well, let me introduce myself, because anyway, sir told me that about it, but just want to give introductions about history about that. So, I did my master's in organic chemistry. So it is in 2009, it's way back. And then afterwards, I joined NMR Research Center, IISc Bangalore, as a project fellow. So I was with the lab for a year. Then the last 2 years, I joined with Professor Surya Prakash. He is working for the small molecular research, and mainly onto the chiral discrimination. I mean, the big task for all the chemists is that when you have a mixtures of enantiomers, when you take an NMR spectra, it won't give any separate peaks. Everything is merged up. How to solve that problems? So in that categories, I have worked 2 years on that case. So we have a couple of pulse program developed also. And all we know that we have 3 methods: lanthanide shift reagents, or we have solvating agents, or divertizing agents. So with the same methods, we can do it, or pulse program wise, we can make any modifications. We have done things on using a diffusion experiment. We have utilized that experiment to separate the chiral centers and these things. And in 2013, I have joined GIAN India as an NMR application specialist. So it's close to 12 years now with the GIAN. So we have a lot of opportunity to interact with our global application team, and we meet with the different application group and working on the different problems. So this is my history about NMR side. So totally I have close to 15, 16 years of NMR expertise in this. Okay, this is my introductions. Let me start with my talk. Okay, so you are already having the 6 days of continuous intensive workshops on the synthetic and molecules, understanding biological activities of fluorinated molecules. Now, we all know that synthesis is one part, and after synthesized one, characterization is very, very important. Whatever you do it has to be identified properly and reported, and you have to make a not only qualitative ways, you have to make it a quantitative methods. You have to prove that this molecule is correct. So in this sense, we have a spectroscopy techniques. We have a different techniques, like we have UV visibles, IR, all these things, and we have a mass spectrometry also to identify that, right? So in that, NMR spectroscopy plays a very important role, because this comes with the where the NMR is mainly onto the nuclear interactions. So when the nuclear is talking about that, you can easily identify it. It's related to all the chemical environmental sites, right? So the NMR spectroscopy is a very, very important spectroscopy technique for the characterization things. So this will be the characterization methods. We are now discussing about that. So before I start with the fluorine NMRs, let me give some brief introduction about the, or you can say, just want to show how NMR spectroscopy is so potential in the chemistry research part. Okay, it has a wide variety of applications in. We take it from the entire scientific research wise. So let's give a simple one. The first we utilize for the chemical structure and dynamic studies. Okay, you have a molecule, then identify whether my synthesized molecule is correct. Identification of 2D structures and 3D structures of that. And even when you have a molecule and you have a targets, how it is interacting, dynamics of identifying the molecule is also important. That part also can be done with the NMR spectroscopy. We have different experiments and different nuclei to measure that. The beauty of NMR is that it is not one nuclei, whatever the elements available in the periodic table all has isotopes, then you can do the NMR measurement. That's interesting things. You can do the mainly chemical characterization dynamic studies. Then you can utilize for the macromolecular studies. Okay, you have nanotubings or big molecule interactions, molecular radii identification, size of that also can be identified through the NMRs. Here again we do it with the NMR active nuclei. We do a proton measurement experiment. Maybe it may be 1D or it may be 2D experiments to identify the interaction between the big macromolecule and with a small molecule. Or if you want to identify the radii of that, we have a special experiment called the diffusion experiment. DOSI we call it is. You can use that one, identify the diffusion coefficient. From the diffusion coefficient, we can go back to the radii. It can be identified with these molecules. This also can be done with the NMRs. And now we have, it comes with NMR, this comes to food industry also. It's very, very important now. In food industry, the problem is adulteration, right? So when you talk about any products, like there may be adulteration. If you take a honey, juice or cheese, anything. So this adulteration process also can be identified through the NMR. How it will be done? Again, it's with the NMR spectra. You have a compound, maybe a food has some materials like amino acid or something else, you have molecule. Along with it, if you have impurities peaks, it has a different chemical fingerprint regions. Identify, matching with the spectra. You can identify that, so with that it has impurities. If it is adulterated, what percentage of adulteration has been done? There are some databases required. You can do some statistical analysis, importance like PC analysis, PLS analysis. The different methods of statistical analysis can be utilized to the food industry side. So now the recent trend in India also, the government has imposed the NMR spectroscopy is the right technique for the honey profiling. Earlier it was not, that it was maybe 5-6 years back it was started with this. Now even the TV commercial advertisement, they were showing that NMR spectroscopy is the screening process used for the honeys. And there are, if you see that when it came, maybe we have many manufacturers make of the honey, right? In that only 1 or 2 manufacturers qualified that is authenticated honey process. So, and drug discovery sites, it is again all this step of process, identification of the molecules can be done with this case, interaction studies. Biomolecular application, of course, this is another interesting areas. But biomolecules consist of the carbon, proton, carbon, nitrogen based chain system, okay. We have a multiple experiment, a multi-dimensional experiment. You can correlate that. A small molecule, one dimensional, two dimensional is good enough. If your molecular size is big, you can have a 3D NMR, 4D NMR, you can make a correlation part. You can do that identification. So that's a biomolecular structure identification. Petroleum product, again it comes with a molecules or mixture of compounds. It maybe you can identify with the what is the naphtha content in the petroleum product. And petroleum industry has different segments. You have crude oils, diesels, petroleums, catalysis studies can be done with this. All these areas NMR utilized. You can do a simple carbon measurement, or you can do the carbon based quantification, you can do that. And proton based quantification, you can do that. And by using the spectra, you can identify what is the naphtha content, how much aromaticity is present, how much aliphatic compound group is present, you can identify it. And interesting fact is that it's not only, it is a high resolution part, I'm talking about NMR. Now, in case of a low field also, no oil well, you have the oil wells, how to identify how much percentage of petroleum content is present. You can send the portable NMR in the oil well, there you can identify this percentage base. How they do it is based on the relaxation, T1 relaxation base, the different methods to identify that. There also NMR is utilized. And agrochemicals, again this is chemistry, there are different kind of nuclei. You have phosphorus, NMR, you can do it. You can utilize for the silicon based experiment, or sulfur, different type of NMR can be done. Toxicology, again it is heterocyclic compounds. You have a nitrogen based compounds over there. You can do the nitrogen experiments. And you can do with the proton nitrogen correlation experiment also, you can do that. And we have all the areas. Now the very interesting fact is now the battery applications, right? The battery is another booming subject now, right? So in the NMR research, we have reached where till we can do operando measurement. In situ battery operation can be identified. So while doing a charging of battery, what is the electrolyte diffusion happens with ions, how much, that can be identified. So in battery we have three electrodes, anodes, cathode, electrolyte. All three materials are made up of the chemicals, right? You can do the NMR measurement. When you have a solid electrolyte, you can do the solid state NMR. You can do sodium based NMR, you can do it. If your battery is lithium ion measurement can be done with that. How lithium diffusion is happening, that can be identified in solid state. If you have solid electrolytes, simple, you can measure that ion diffusion, dosy experiment, and different method of experiment to do it. You can do a battery application also, you can do that. While charging, discharging one, we have made a probe such over that in the probe itself you can load your battery assembly, you can supply the voltage current. Then you can identify how these ions are diffusing, so the variations of the ions that can be identified with this. So a lot of applications can be done with NMR spectroscopy. So okay, let me go to start with this understanding. Now first question comes, what is NMR? It's nuclear magnetic resonance spectroscopy. It's a spectroscopy technique. Extensively utilized for the chemical substance characterization and in non-invasive techniques. Here whatever sample taken back for the further reaction. You can do that. There is no distraction. If you take a mass spectrometry, you cannot take back the sample, it is gone. In NMR not like that. You can take back the samples. That's why we have a big application called MRI. So MRI is also based on the NMR principle. The sample is human body or something. You can send it inside. That's what we do it. And you can do most element can be identified. You can do with the proton, deuterium, carbon, phosphorus. This all the living organisms, whatever you have it, all the elements. This is available. It can be identified. Even oxygen, nitrogens. This can be identified. All that in NMR. Molecular dynamics, reactivity can be identified. Let us understand a little bit about that. I will not go in detail about how spectroscopy works because you already have some coursework. Maybe some fresh students might require some brush up, whatever learned from the graduation. So in NMR, it's basically nuclear magnetic resonance. So when you take a sample, every molecule has the atom. Atom consists of the nucleons, right? So in the nucleus, if you have the nucleons, combination of odd number of protons and the neutron, it's act as NMR active. There should be some spin value. If you have a spin value, that is NMR active. Okay. So now there are like example like hydrogen, it's only one protons. Carbon, again you have the neutron and proton, but it's odd combination. Again, so your total atomic mass number will be a 13 is active and 12 is a proton numbers. But when you talk about the C12, it's even combinations. That is not NMR active. Okay. So the spin values where it becomes 0, this is basically resultant spin angular momentum of the nucleons. If it is 0, those are not NMR active. Where spin value is present, those are NMR active. So what happens, it lacks, like when you have a spin, of course there is a fundamental property called magnetic momentum. So when you take it in the gyro ratios, the top equivalents, when you take it in the earth magnetic field, it again rotates. That is a lump position. Now this tiny magnet, if you place it in the NMR, any external magnetic field, okay, then it has there's a torque presence. One is I value spins, just imagination, and again when you place in the magnetic field, it feels as torque, okay, because of the external fields. Then there is a precision that is called the Larner precision, okay, that varies with the nuclei to nuclei. Now this is an example here. When you sample outside the magnet, it's all randomly oriented. Well, it's randomly oriented. So, sorry, it's annoying noise. It's a randomly oriented nucleus. Of course, molecules are movements with this. When you place it in the magnetic field, there is a force. Okay, some will be aligned to the magnetic field, some will be opposite to the magnetic field. Again, depends on the energy state, depends on the I values. If you have a half, there may be 2 energy state. If you have 3 by 2, a different energy states will be there. Okay, so energy. So this is external magnetic field. Now here again, so this is energy states. This energy gap is very small, very small it is. Okay, and so the population difference is also very small. So when energy gap is very difference is less, the nuclei can present in the ground or the upper state. The difference is very less. Now this energy gap is exactly matches to the radio frequency. Okay, so then only this will talk. When you apply the radio frequency onto this, then there is an excitation process happens. The lower energy state nuclei goes to higher energy state, higher comes to lower energy. There is excitation. This is the one. Now just the difference talking about it. If it is high field NMR, now the difference is very less. You can take it about almost this is almost 1 gigahertz magnet. The difference between the population is almost 10,000 nuclear wise. It's a very low sensitive technique in the cases. Okay, this is the basic principle of how NMR works. Now again, the energy gap depends on the nuclei. Nuclei has a property called magneto-gyric ratio that depends on the variation happens in these cases. Now this is how magnet looks like. So you have two excellent in system here. One is 500 MHz NMR, another one is 600 MHz NMR instrument. So this is how it looks up. Somebody's first time doing the NMR, you can see this is a magnet, superconducting magnet, and it is the spectrometer and is a computer. So now there is a probe, your whole RF assembly sitting here that will be loaded into the magnet downside, and your RF coil is present in the probe and sits in the center of the magnet outside the magnetic field. Okay, the whole entire magnet phenomenon happens over here, NMR phenomenon happens over here, and everything will controlled by the RF assembly. This is called the console or a spectrometer. Then it will be here. So whatever the supplied will be based on the current has the parameter called the amplitude frequency phase that will applied, and when it comes back to that, it comes as analogous signal. But as a computer cannot read the analogous signals, it has to be digitized. So it will be digitized, and the conversion method called the Fourier transformation from the time scale to a frequency domain, that will happens over here, and you will get a spectra out from this. Okay, this is how the NMR works in principle. And the field relations. Now as I mentioned, so the energy gap is too low, the energy sensitivity is low. How can I increase my sensitivity or the field relation? If I increase the magnetic field strength, energy gap increases and increases in power. When energy gap is increases, there is a population difference is increasing. When population difference is increasing means you are increasing signal to noise ratio. That's why people looking for high field NMR for the bigger size molecule. If you have protein or something where it cannot be resolved in the lower field, it can be resolved in the high field one. There are two problems in NMR. The one is a resolution, second one is sensitivity. To solve that, okay, so we go to high field NMR. Now here's an example here, a small molecule, ethyl benzene. So if you record 60 megahertz, all protons here aromatic big single peak because resolution is too low. Then go to field higher and higher, everything resolves out here. Your metaproton, ortho, paraprotons get resolved out. Okay, the resolution can be achieved. So that's why the biomolecule has a big size, right? Lot of protons are present. To resolve that, you require a high field one. To get the high resolution, high field NMR. And sensitivity, second part is that. Again, so when you get a samples to increase the signal to noise ratio, the two way to do it. One is adding more concentration or more samples. But that is not possible for a biomolecular case or something like when you have very precious samples. If you have inorganic material, you can get a 1 mg, 1 gram samples as okay. But when you go to the biomolecules, getting 100 millimolar concentration is very difficult for them. So how can I boost it that? The only way is the sensitivity has to be increased. There are some probe techniques called the cryo probes we have, and different type of probes are available. Now his sensitivity problems. So now you can see using high field NMR, you can increase signal to noise ratio also and resolution, both can be improvised. So they just want to summarize on this point, the NMR is insensitive, very low sensitivity. To increase the sensitivity or low sensitivity resolution, you require high field NMR. Okay. In most of the kit, in general application, if you have 400 to 500 megahertz NMR, you can run the molecular size of around 2000, 3000 molecular sizes you can easily handle it. But if your molecular size is increasing higher and higher, it becomes like 5000 or 10 kD, 15 kD, 20 kD, you require high field like 600, 800 megahertz NMR with combination of the cryoprobe. Okay, this techniques. Basic. And next comes to that, now let's go to the, now this is, I'll not deep about the instrumentation side, let's go to the application side now. So NMR, when you get NMR spectra, these are the parameters can be obtained. The one is chemical shift. What is chemical shift? It's a frequency scale basically, okay. All based on the chemical environment, you'll get individual separate peaks. There is a chemical shift. And spin-spin coupling based on the neighboring effect. Suppose you have some in NMR, all nucleus are active. So I have proton here, I have proton here, the proton can interact, talk to each other. So then makes it peaks, supposed to come a single, it may be doublet. Or that depends on number of nucleus present, big splitting patterns. So there are spin-spin couplings. And that gives information about the neighboring environment. Then intensity of signals. Again, intensity of signals gives a number of responsible nuclei. Suppose you methyl has a 3, and if you do area under the curve, if you do the integration for that, that gives a number of protons, number of carbons, number of phosphorus. And relaxation is another important parameter, T1, T2 relaxation, spin lattice and spin, the transverse relaxation part, both. Okay. So this gives information about the molecular size and molecular natures. Okay. So that will varies, T1, T2 will varies. And NOE, overall effect, so the spatial correlation can be obtained. And dipolar and quadrupolar couplings are based on the nuclei. If you have a high spin values, this both are comes into the picture. Okay. So now importance, now how NMR is utilized for the pharma industries. Now pharmaceutical industry, you can do API measurement, you can do that. Okay. Then you can do the quantification of impurities also can be done. And if you have excipients and API mix up. Okay. So then if you want to separate these two, virtual separation of course, it's not a physical separation, you can separate the peak, you can identify the excipients and the API. Suppose you have two APIs are present in over there. If you want to identify that's how many APIs are present, you can do the experiment, you can separate the components. Or you have something that can be identified. This is one thing. And analysis of all the drug product, drug polymorphism is very important here. So synthesizing, then you have solid state, you might have a dimer formation, trimer formations or interaction between that can be identified. Quantification of purity, co-crystals, salt formation, solvating properties can be identified through the NMRs. You can do that. Okay, so now let's go into the fluorine NMR. So, but I don't think so this slide is required because already you have detailed talks for this. So fluorine has a very important role in the chemistry research. It can give add-ons to the different properties like polarity, acidity, reactivity sites, and it's widely used in pharmaceutical, agrochemicals, material science application can be done. And the fluorine important thing is a very strong electronegative atoms, okay, and it has the very smallest substituent replace hydrogen nucleus. When I have fluorines, it can have a steric effect different, polarity is different. This gives interesting things. In concern to the NMR, okay, let's drug molecules, you have seen that most of the drug molecule have a fluorine nucleus. You can see that almost 25 drugs are containing the fluorine ones and different places utilized. Now when it comes to the NMR side, how fluorine will be utilized, how the fluorine is active. The interesting fact about fluorine is a spin half nuclei, okay, I value. When the I value is very less, then the measurement becomes very simple. Spectra becomes more simplified. That's why proton, carbon spectra are very simple because I values are half. When you go to boron NMR, analysis is not this easy because 3/2, that is spin value is higher, then the quadrupolar effect will comes up in the picture. So the spin is very easy to measure that. Interesting fact is that abundance, it is 100%. It's like a simple like a proton only. The measurement is very high measurement easily. And comparing the relative sensitivity versus proton to a fluorine, you can see that it's almost 0.83%. This if you take one is highest and this is one. Next highest abundant nuclei for the measurement sensitivity wise is a fluorine compared to proton one. Now you can see that property wise. So here proton is one of the most utilized nuclei for NMR studies. because of the abundance and the I value gyrometry ratios, and this is the main things. Second one is the carbon will be that carbon is a less abundance, of course low sensitivity, but when you have low concentration, low mixture concentration has a difficulty to measurement, so on. Nitrogen again even lesser abundance. Now nitrogen has a two isotope, nitrogen 14 and 15, correct? The 14 problem is a quadrupolar nuclei. The measurement becomes a very difficult and sensitivity lost over there. Okay, peak becomes very broader. It goes buried under the noise level. Okay, that maybe now the recent techniques has been improvised for the enhanced sensitivity, and those different techniques can be utilized for the make it a better signals. And the abundance is very less. And here good part is frequency separation is a larger one. So when you have different molecules, can be seen separate peaks over there. Okay, but in case of proton, the ppm separation is 0 to 13 ppm. All peaks comes in one place. It may be merges. And a fluorine case, the spectral chemical shift range is a wider. It's close to, you can say that 350 ppm range, plus 50 to minus 300 ppm. So if you have make a small changes in the molecule, still the peak becomes separations, well separated peaks. Okay, so that can be identified in this one. This is an interesting fact about a fluorine. You can utilize for your most of the research part. So chemical shift, as I mentioned, you have different type of molecules are present, then it spreads over that. Make a small changes. Now you have one fluorine over here, so the two protons, the chemical shift is here. Now we just removing one of the proton, introducing another fluorine to this, chemical shift, look at this, the huge difference, that is shielding effect and de-shielding effect, difference variations, the larger variations. Now another important thing is, now simple fluorine measurement is okay, but now when a fluorine is present in my molecule, then if I measured another nuclei, carbon nuclei, this fluorine makes a problematic, as like a proton only, highly abundance, right? It interacts this. The problem is, when the fluorine is present, now a molecule of fluorine have carbon attachment, the fluorine and carbon coupling is very, very strong. Now look at this, here is the coupling constant values mentioned for that. Now if you have a fluorine couplings, there is no direct bonding, there is no molecule like that fluorine present, it may be two bond, the two bond coupling is 400 Hertz. Okay, it looks like, if you have 400 megahertz NMR, it looks like 1 ppm difference almost, the fluorine coupling values itself. If you have two, coupling will be two larger one. So 3 bond will be a 150 Hertz. The problem here is I can see fluorine carbon coupling. The 1 bond coupling goes to 150 Hertz to 250 Hertz. It looks like half the ppm difference, almost of 1 ppm difference. Now when I have molecule, the fluorine is present, it makes it complicated. When you record a carbon NMR, it's because two separate. You will get an ambiguity, difficulty that whether it is two separate peak or whether it is from the coupling from the fluorine. That is a big problem. So unless you remove the fluorine couplings. But as a practical, you see, when you go to instrument, proton and the fluorine goes in the same channel. Okay, instrument, let me explain a little bit about this. Two channels you have. Channel 1 you have proton, fluorine, another channel goes for the broadband. Okay. Now if I want to do I can do only one decoupling one time, not simultaneously, I cannot do that. Okay, because both frequencies has to go together, right? Difficulties. Now in my molecule I have carbon has a coupling from the fluorine and the proton together. If I do a proton decoupling, the fluorine coupling will comes into the picture. Peak becomes separated. So that is a little bit difficulty task. So for the chemist, and sometime you'll get a and problem is splitting, signal to noise get reduces huge. That is a problematic, especially for the CF3 groups where I have the junction carbons, where the fluorine is present, that carbon will not come up easily because of the one is a fluorine coupling, second one is the splitting patterns to I, that is a big difficulties. So this is the coupling patterns. So the two bond coupling is very high, and fluorine and carbon is 10 to 40, and the 3 bond coupling is 0 to 10 Hertz. And the phosphorus and fluorine coupling is again is a very high couplings, but these are the very less. Here not much difficulties, because you may be having one phosphorus or two phosphorus in the molecule, then easily can identify with this. But only problem comes for the carbon sides, where so many carbons are present and one fluorine is present. It can go to 1 bond coupling, 2 bond coupling, 3 bond coupling. It can go to the longer range couplings. That makes a complexity in the spectra.
But then the 13C abundance is also pretty low.
Yes.
But then if you talk about the proton, it has also a strong coupling, right? So it's 0 to 100, and that is almost like 10 to 40.
Right.
But then if you go for the abundance, like proton is always equi-abundance with the fluorine.
Right.
But in the case of 13C, that's very, very low.
Very low. Very.
If you are talking about a small molecule, so the abundance, would that also determine in the, the actually seeing in the splitting of those?
So the good question. Again, thing is the carbon NMR upon is 1.1%. Now suppose a direct bond fluorine couple, the doublet. 1% split into 0.5. It's too large. The problem is everything buried under the noise. Now we will get difficulties whether I have a peak or not peaks. If it is now I mentioned one. Suppose I have CF3, 3 fluorines are present. It means a quadrant. The one carbon gives a 4 peaks. That's again everything buried under. You will get confused. Suppose I have lot many carbons. This quadrant is like a 200 hertz. One small here, one somewhere here, one somewhere there. Then you will get difficulties whether it's a separate peak, whether it's a coupling one. The really difficult task for the again assignment of these carbon structures. Okay.
But the adjacent proton will also make the splitting, right?
Splitting. But in general case, carbon NMR will be a proton decoupled carbon. So like two channels, carbon goes in this channel, proton goes in these channels. So I can make a decoupling. The carbon observation time I can do with the decoupling of the protons. But the problem is fluorine coupling will come in this case. But anyway, I have interesting solution for that. I can show it in the later stage where we can do a enjoy with the single carbon signals with this case.
But the other thing is the CF coupling can be felt like 2-3 carbons away. So the magnitude of the coupling kind of decreases with distance away. And so you might have a trifluoromethyl, and you see the quartet really clear on the first one, and the second one you get further down, and now you have a fully substituted carbon that's already tough to see. And then you have this quartet, and you're like digging in weeds there to see if there's any.
Yeah. And if it is a peak is merging, then everything is even difficulties. So where it is coming up these cases.
Good students can do it. Good students can do it.
Okay.
They want to finish it, think about it.
Yeah. So gyrometric ratio similar like a proton 1, highly abundance 1. Okay, this is some of the examples how the fluorine chemical shift varies with the a substitution part. Now if you have some just CF3, look at this is minus 68 ppm. Now it's maybe you can say full of shielding or something. Then you have replaced one fluorine with the proton. Again, look at a chemical shift variation, minus 100 ppm. So it's a huge difference. Then replacing with the two protons, the fluorines with 2 protons, it becomes 200. It's a shielding one cases. It's a large separation chemical shift. This is why interesting. Fluorine has one small, has because of steric effect or polarity effects, small changes make in the molecules as can be reflect on the fluorine spectra. It can be seen that. Interesting. Now in here is an aromatic systems where you have in the second rings you are changing the substitution part. Still there is a variation happens with the chemical shift of the fluorines. You can see that when you have a just simple with this proton here, so then you can minus 220 ppm, and if you have with the methyl in these places, then it becomes a minus 313s. There is almost a 20 ppm, 10 ppm difference over here. So this is interesting. Now you are known only about a proton carbon correlation methods. Now I suggest is why can't you do with a fluorine carbon correlation experiment? It's an interesting fact that you can work complete assignment different molecular sites. So this is what I want to say that small changes in the molecule can introduce a lot of frequency difference between the individual peaks. This can be taken into these cases. So and the solvent effect, that again there comes sometimes your molecule dissolved in different solvents. But in the fluorine case, changing a solvent not makes much difference. If we take most of the case we take a CDCl3 or DMSO or something. Changing the solvent maybe introduce 1 ppm or 1.2 ppm maximum can change. We don't consider as NMR, this is must changes happen. But in case of proton, there may be a lot of changes. No, when you take from in this case here in the molecule, look at this molecule you are here, CDCl3 peak minus 76 ppm, but same thing molecule taken with DMSO, it's minus 75 ppm. So the difference is very small over here. But in case of the proton, so it becomes a 5.82 ppm and then it becomes acetone becomes a different 1 ppm difference. It is a large difference for the proton cases. So what I want to say is in the solvent changing, the fluorine has not much effect on this, but proton can be seen that effect on the cases. So here, let me go to the examples now here. I have a small molecule over here. Here it is, you can say 1,1 substituted 2,2,3,3 hexafluoropropyl ethers. Now you have a 3 fluorines, 4, 1 here, here. Now if you take a simple proton NMR, how many signals can expected here? In this molecule, how many signals can be expected? Proton signals. 1, 2, 3, but I have shown only 3, 2 here, the another one is somewhere here, and of course it is the shielded area, so I have not shown because I want to show some of the interesting fact here. Now this is how many splitting will comes? This is a one quadrate, okay, because of methyls. But there is no effect transfer because of heteronuclear over here, it won't transfer the couplings over this. Now in the case of this one proton over here, now proton you see one proton becomes a lot of splittings over here. The why is happening because of this fluorine coupling plus doublet will happens and plus this fluorine and this fluorine coupling on this proton becomes a lot of complexities. So same thing if you do the fluorine NMR cases, there are three peaks. One fluorines over here and another two you have fluorine methyl CF3 protofluorines over huge signal, you can see that shielded one, and you have the two fluorines because of this proton coupling is present. Now you can see this fluorine has behave different, this fluorine has a different, you can see two doublets over here, you can see that. And this is also, there's a, look at the patterns over here, it looks like a, this is called, we call it a strongly coupled spin systems. Some, because when you have a chemical shifter becomes closer and closer, peak becomes same positions. When you have slight variation in the chemical shift, you can say magnetically equivalent or chemically almost equivalent, magnetically non-equivalent, there will be slight variation. So coupling value is higher than the chemical shift, those are considered as a strongly coupled spin system. Okay, this is called roofing effect or equalities. This is, you can see the feel it here. These two protons, the fluorine case, this is a fluorine. The widespread here, you can see that. Now let me zoom the problem now here. So this CF31 all becomes a huge couplings over here, and this fluorines has this splitting patterns. One is the proton coupling because it looks like this same exactly same replica here, it is a proton coupled. And other effect are this fluorine coupling and this fluorine coupling onto these, it's become the splitting patterns. Okay. Now if you want to achieve this good resolution side, you should require something like a fluorine with a proton decoupling part. So you can get the only the homonuclear coupling patterns, so only fluorine spectra can be seen over here. And this splitting is because of the fluorine couplings, it's not the proton coupling sites. You can see that. So this is basically you can call it as multiplets, it's not be exactly a patterns can be identified.
So during, as you have already mentioned, that one at a single time we can do only one decoupling,
Ha,
right?
ha,
So when we are doing this proton coupling over here
ha,
during 19 years,
ha.
so can't it be 13C will be interfering this?
Yes, it's a good question. Yes, in this case, carbons interfere. Now you should tell me that. Now question is, you have molecule complete, right? So what is the carbon abundance? 99% will be C12. 1.1% C13s. Yes, in your spectra you have 13C coupled. Unfortunately, fortunately, the peak is buried under the noise. You have two groups. Whatever you see in a peak, it is a C12 attached to fluorines. Okay? You got it? There are two type of molecules here. One is a 13C attached fluorine or fluorine. Another one is C2 attached fluorines. C2 is NMR inactive, that cannot be given. That's a huge peak, 99%. 1.1 will be the C13.
I think if you increase the concentration or if we just record it for longer hours, that might also show up and the peak
It's
even
not
more.
required, sir. In the same spectra it is there. I have to zoom it up.
Oh,
if you
okay.
see a simple proton NMR, you probably see the satellite peak. We call the NMR terminal satellite peaks. Just to zoom it up, that's a carbon satellite. Measure the distance, you get a proton carbon couplings. Maybe 150 Hz, 130 Hz, depending on the coupling constant. It can be seen.
Also, what will be the effect in quantitation when we are decoupling? The
Yes.
intensity.
In quantification, we always say that decoupled exponent is better one. You have decoupled a carbon over here. Now, okay, you are talking about a fluorine quantification here? Yeah, fluorine quantification side also, when you do that. So we are taking, this is a peak for the 99% of the C2 attached to fluorines, okay? You are missing out of the 1.1%. That's also contributing for the quantification. Now, when we say that a quantification, you have decoupled the carbons. While observation of the fluorine, decoupled with 13C, so that whatever the satellite adds on to the center, that becomes single. So you will get a complete whole molecular area can be seen over here. So coupled spectra is not 100% quantified. Decoupled is a more quantified process.
So when you try to use quantitative, when you try to quantitate with NMR, you need to set your delay time to about 10 seconds. So some of them don't, yeah, if you stop it at 3 seconds or 5 seconds, some of the Fluorine nuclei will not fully relax, and then you don't get the full signal. So you've seen like alkenes, you take a lot of NMRs for like a normal alkene, sometimes those peaks are only 0.6, 0.8, they don't integrate to 1.0. That's because you have not fully relaxed, you haven't given enough time
Qualitative measurement, quantitative measurement. Qualitative requires some special parameter has to maintain. One is majorly relaxation. Okay. So we always say that ideal procedure is you should measure T1 value of the fluid first, then multiply 5 times of the T1. That value will be your relaxation parameter. Because you are using 90-degree pulse. Again, this order 45 degree. Okay, let me talk the 45 90 degree means my magnetization is in the Z direction. My receiver coil is here. I'm tilting this magnetization to the receiver face is called the flip angle. Okay, so this is the flip angles. Now what happens when you do normal NMR? These are highly abundant nuclei. But if you apply 90 degree, you should wait the 5 times of T1 to relax back. It's a long time. But qualitatively, we don't want to wait that much of time. What we do is we apply only 30-degree angle, flip angles. Okay, we take the projection of that. That is enough for the qualitative measurement. Okay, but yeah, what is the gain will be the relaxation times are less, maybe lesser times. But quantification, this is not going to work out. You should apply the 90-degree pulse, fully flipping. Okay, then wait all the nucleus to relax back. Then start second pulsing. So this is a qualitative. But how do I know this? Every nucleus has a different relaxation, T1 values. Maybe a CF3 may be different, CH2 will be different. Then to measure that, the right method is measure the T1 calculation. The experiment is called the inversion recovery method or saturation recovery method, experiment templates. Now these are the robust or I can say the modern spectrometers. If you want to put a QNMR, Q fluorine, the recent template is ready. Select the experiment, submit it. Automatically it will calculate the T1 first. Then takes a maximum T1 value in your experiment. Then you visualize.
I agree with everything. If you go to 10 seconds, you cover all the different fluorine types of fluorine atoms. So that's like the really thoughtful way to do it. But if you just want a program that covers a whole bunch of different types of fluorine, regardless of what's in your molecule, we just say 10 seconds covers it all. So, but that's the right way to do it.
Yeah, this is what to do. That's why the integration when you measure normal, you will not get an exact number of integration numbers. That's because of the relaxation effect in these cases. Yeah, this is the things can be done, proton fluorine. There are some special techniques or the probes are available to do this kind of things. As a first I told the going of two frequencies, same channel is a difficulty part. Now the recent development from spectrometer in the probe side where you can handle both the frequency together. Let me go to the real problems here. Now I have same molecule, if I measure the carbon experiment, simple carbon without any decoupling one. All carbons, you need this carbon splits a quadrate because of these fluorine couplings over here, somewhere here, and plus this carbon splits because of this fluorine coupling. And again, this is fluorine impact on the carbon also over here. There is a couplings over here. This is, you look at this here, lot many peaks plus signal to noise ratio is completely decreased. Okay, this is not acceptable for the regular operations or the assignment strategies. So that's why we do with the proton, carbon with the proton decoupling. So at least you can gain it. But in this molecule, there is no gain for you here. So no, you can apply this proton can be removed over here, but the fluorine couplings will be present. Okay, so you can see, look at these areas over here, a lot of splittings. Now you require something like this, where a carbon, proton, and fluorine simultaneous decoupling, so that I should get all single peaks. Okay, but this problem is there are 3 nucleus measurement. At a time 3 nuclei has to go inside. A routine spectrometer, this is cannot be handled over here. This is case. But yes, there are some special techniques or probes that are available to do that. So this probe I hope you have in your facility in these 600 MHz NMR cases. So we need to check that. So but in the 600 MHz this facility where you can do this experiment, carbon with the simultaneous proton fluorine decoupling possible to do that. Okay, so let me just give a brief introduction about spectrometer. I'll go to the again applications now. So we have a very new series of spectrometer called the luminous series spectrometer. So this is how it looks like. Probably in your case maybe a different spectrometer one, the previous generation one, and is a very latest one where you have a most advanced digital and the high frequency technology. And interesting fact is multi-resonance measurement is possible in the standard configuration side. So let me go to that. So like, okay, this is my spectrometer. Now my 2-channel spectrometer I have. 2 channel means channel 1 output, channel 2 output, okay, 1 frequency. Now in this spectrometer, luminous series spectrometers, all that, and especially for the your NIPER instrument also has the same facility. Actually, one output you can apply the 4 frequency. Another output you can apply the 4 frequency. It can be handled spectrometer side. Okay, example wise, if I have something like this, I can have second channel can have carbon and first channel can have proton fluorine together, can be applied. Now then let comes to the application side. Of course, here 3 nuclei. To handle that we require a special probe called Royal HFX probe. Okay, it is basically 2-channel probe, but it can handle the 3 nuclei together. Okay, while observation of the carbon, maybe proton fluorine decoupling is possible, or while observing a proton, you can make a fluorine carbon, both decoupling is possible to do that. It can handle Royal HFX probes. Okay, the Royal HFX probe is basically a 2-channel probe. Channel 1 can take care of the proton and the fluorine, and channel 2 can take care of the phosphorus to nitrogen, completely a broadband range. It can be handled. And in this probe, you can do a temperature range from -100 to +150 degree. You can do that. And tuning and matching is completely automatic. You can do that. And specialized experiment, as I was talking about that earlier, it was not possible, but it is possible, like a proton fluorine decoupling, fluorine with the proton decoupling. Interesting is carbon with the simultaneous proton fluorine decoupling is possible to do that. It's not only for a carbon, you can use any X nuclei, because I mentioned it is LF is basically a broadband. You can use for the any nucleus here, X with the proton to fluorine. Now interesting experiment like HMBC, suppose your earlier days proton carbon HMBC means just proton carbon correlation, but while doing, if fluorine is present, it makes a disturbance. But with this Royal HFX probe, while direct observation you can make the fluorine decoupling, and in an indirect dimension you can make the fluorine plus with the proton, both decoupling is possible to do that in indirect dimension. All the carbon gives contour gives a very nice one single contour, plus the acquisition time is reduced much, because the signal to noise ratio boosted by the because of decoupling part. Here. So okay, here is an example. Now I have some working on his old samples over here. This is basically a drug molecule over here, where you have the aromatic, the 3 fluorines are there, 2 fluorines added in the aromatic, another 1 fluorine is for the heterocycle, this ring. Now if you do simple carbon experiment, now you see aromatic peaks, all the carbon signals becomes a splitted lot of things here. Let me zoom that area, you can see that. Now the two problem, one is the splitting is more, second one is signal to noise ratio is very, very less, because one peak you can double it. Okay, one. So this is very difficult for assignment sites. But with this Royal HFX combination, you can do something, this experiment, carbon with the simultaneous proton fluorine decoupling, so that I can remove all the interaction, fluorine and proton interaction, all signal becomes singlet. You can get a very nice singlet. Signal to noise ratio much, much better. For me, that is interesting here. Earlier days, you have to spend for the 5 hours, 6 hours for simple or carbon measurement, and this can be reduced a lot. Plus, complexity has been reduced a lot, right? It can all carbon become single peak for this. So same. Now I have a small molecule to show that. Okay, this is very simple. The fluorine bromo attachment, chloro attachment to this molecule. Okay, how many carbon signals we expect here? 6. Simple 6 carbons. But how many we are getting this? When you record simple carbon, you can see that so many peaks here, too many. This is a simple case I showed. Suppose this same group is attached to some another group of organic groups, then spectra becomes more and more complex here. Now this is basically a 2 peaks. This is because of this carbon fluorine coupling to the directly to this carbon becomes a long range. Sorry, 1 bond coupling, very strong. It's maybe a 250 hertz or something like that. Then the one of the peak is no splitting at all. It's because of there is no much. This is a case somewhere. Yeah, sorry.
That intensity is high because it is too.
There is no coupling effect on this group. Basically, is everything singlet. So you can say that fluorine has no basically this is meta portion of the carbons. There is no effect seen onto this carbon. Now you have the 2 peaks. Maybe this is a 1 ortho positions 1, and second one is para positions 1. That is a strong coupling. You see, this peak also got splitted over. If you see, look at if you zoom that area, there is a splitting. It's a long range fluorine coupling between this fluorine to this carbon couplings. There is a. Fluorine has a strong effect onto the multi-bond couplings. I mean correlation, or you can say coupling constants. So this fluorine is not only effect onto the direct carbons, it has impact on the next bond, 2 bond, 3 bond, 4th bond also it can go coupling.
But why doesn't it do in the meta plate because of its?
Maybe the electronic density or something. Coupling patterns goes to the bonding electrons, passes through the bonding electrons. Now there is a deficiency or something electronic triggers, so that is not able to see any kind of the effect onto the carbons in this case. There is no effect on fluorine couplings on these cases. So there may be a slight, if you zoom it also you will not able to see it, because the spectral resolution itself is a broader area, because the line shape of the carbon is quite high compared to the proton bond cases. Okay, relaxation effect. So there is no.
Yes, Srinivas, can you also explain the delta, like that variation and reasoning we used to?
These cases.
Like 115, 123 and 131.
chemical shift frequencies. Yeah, so it's the fluorine direct bond coupling. It's an electronegative atom, right? This is of course becomes a deshielding, highly deshielded part. So this is a basic. Okay, if you go to this areas, this is called the upfield, or you can say shielded areas, and this side comes to the non-shielded, or you can say deshielded areas cases, right? So when you have electronegative atom attached to these carbons, there is all electrons are pulled up. The carbons, the nucleus becomes more exposed to the magnetic field. It can give frequency, it can absorb more frequencies. Maybe its energy state may be larger compared to the methyl or other cases. So that's why the frequency is a larger area. That's why you can see that 150 ppm carbon sequence over here. And splitting is because the fluorine, one fluorine is attached to the carbon, so it gives you can see doublet. And thus fluorine has again 2 bond coupling and good 3 bond also, but again this depends on the bonding network electrons. Okay, all coupling patterns goes through that. So you cannot see it.
Something I see that is the strong intense one, that is actually the meta to fluorine, that is this side, but then the
Yeah, I also think that is what I was thinking. Maybe that the one carbon which is attached to bromine, maybe this is that right? That's what you are saying?
No, this is the one basically. You call it. Am I wrong? Assignment?
no, means if we are only seeing the, so there are 2 things. One is, okay, the fluorine also plays roles, right?
Yeah.
That's right. Fluorine also plays roles. We are negating that. So that has also its donate direct. Yeah. Exactly. No, that's okay. It's not so simple.
I think go to the one last spectra for you. This will be easy. So now you can see this is now where proton fluorine decoupling is applied. So this has become a singlet. Now assignments become much easier for this. Is all splitting goes off. These cases. Okay. So this is can be done with these cases. It's not only 1D. If you want to do with the fluorine and the carbon correlation, now suppose you have these difficulties, we can go to the simple HSQC. 1D is enough, and if you want, you can go to HSQC based one, fluorine carbon HSQC. Okay, and that is will give clear identification. Or you can go to the HMBC, fluorine carbon HMBC. HMBC is basically multi-bond correlation spectra can be done in these cases. So this can be an interesting application can be done with these cases. Now another example over here where you have a phosphorus is present over here. You have triphenyl groups over here, and now 2 benzene rings have the full of the fluorine attachment. Now if I record the phosphorus for this molecule, how many peaks I expect? Should come only 1 peak, right? So because of phosphorus. But if you see, simple phosphorus makes a lot of complexity over here. Why? Because there are 2 fluorine here and 2 fluorines over here, and it becomes, this is again the pentate. You can see if you talk about simple multiplicity patterns, pentate. And plus there are 2 protons are also here contributing to this. This becomes a lot of multiplicity, you can say multiplet peaks, you can say, one complex peaks individually. Now if I do a proton decoupling for the same molecule, I can remove the interaction of this proton onto the phosphorus, then I can see this is a peak spectra. Why this splitting? Because of this 2 fluorine and this 2 fluorines. It is a 1, 2, 3 bond couplings. This is strong enough. It gives a splitting patterns. Now you can do a phosphorus, a proton, fluorine simultaneous decoupling. It becomes a singlet peaks over here. You can see that. So these are the interesting things you can do it with these cases. Like you have a different experiment, like this is basically another experiment for another molecule. It is a proton carbon HSQC experiment. Okay, 1 bond correlation. Now again it makes a complexity when you have a fluorine is present, like similar like a protons, it becomes multiplicity. Then you can do something like, while doing indirect dimension of the carbon, you can do a fluorine decoupling and plus proton decoupling, both together has to do it. You can do that. And direct dimension, you can do the proton observation, but while doing a proton observation side, I can apply the fluorine decoupling so that I'll get all peaks becomes a singlet for that. Contours can be seen this. So this is something interesting experiments where you can do it. I hope you have the same facility, you can utilize that cases. So now I have one of the molecule, same molecule of complete assignment, I have taken that. So you can say, of course it is a published application note from our group, so I have taken the same spectra to showcase that. So it's one of the drug molecule where you can see that. So again you have 2 fluorines over here, fluorine here. If you do a simple proton may be very simple for it. If you record a proton spectra for this molecule, you can say very clear, nice spectra, very easily to assignment that. But this is not enough, and there is not much on this proton. Of course there are proton, but it's not enough proton to showcase that. You require some additional supporting 2D experiment also. Now you see that there is a proton over here, and this proton and this all where you have aromatic sites, this fluorine has a coupling partner. So you can see that the splitting patterns over here and signal to noise is reduced and plus here also. Now you can do a proton fluorine decoupling experiment so that you can remove all the fluorine interactions. Now this protons over becomes, you can see that very nicely. So this is interesting when you can mention that if you do a fluorine decoupling, at least you can identify which areas of this is interacting. It can be seen that. So now here also becomes signal to noise is much increased, and this is the protons of the fluorine coupled area sites. Let's zoom that areas. Now you can see this is how it impact. Now you have the 3 protons over here, and this is a coupling. This coupling is because of this fluorine coupling to this proton. Okay, and same thing, this fluorine is not only here, it can go to impact over here and here also. You can see that here in the cases of the 6th protons over here, you can see it has an impact here. And if you have a 5th protons, again you have the impact on these cases, coupling partners. These couplings can be removed over these identifications. So you record a simple proton and you can do the fluorine decoupling experiment, you can see splitting patterns easily. Identify this, which areas of the proton has an impact, it can be seen. You can go to this.
Those small peaks, that is the satellite and
With this one?
Yeah, this side also.
Yeah. This is basically satellite peak has a to large distance. I believe this may be some impurity peaks. You can see that. And when you have coupling, I don't think it comes to very closer. Somewhere it will be here. Symmetric. Both the sides will be symmetric. Satellite peaks. Satellite and spinning sideband. There are two things in the NMR side. Spinning sideband. There are 2 satellite with the downside peaks will comes. One is sample is spinning, because of sample spinning will get a spinning side bands. It is not a genuine peak, okay? It's, you can say, instrumental peak, you can say that. And satellite peaks are low Gyromant ratios or carbon coupled one or any other NMR active nucleus coupled to that. That is called the satellite peaks. It comes in the base of the noise in the cases, okay? If you zoom it, you can see those peaks. You can see that. So now in the carbon NMR also same thing here. Now a lot of splitting over here for the carbon of the molecules over here. Okay, it's very difficult to make the assignment when you have these ones. Okay, you may be required some expertise in that, or you require a lot of time to assignment. But instead of that, we suggest now a new technique has been come up where you can apply all the decoupling. You can identify the simple directly attached carbons one, this carbon and this carbons, and again this carbons again. You can identify that's very clearly in these cases. And this coupling also, you see this is coupling is again the strong long range couplings. It is not a one bond is one, second one is a long range couplings makes another problematics. So noise levels in more over here. This can be increased.
yeah, Srinivas, I wanted to little bit because there is a doublet of doublet, right?
Yeah.
Then, otherwise, they are like the 2, since like 4 carbons, and now after decoupling,
It's
see only 1.
one. Yes.
So,
Yes.
so that means, so it will be very useful for.
So there is a 2-bond coupling also over there. It's maybe you need to zoom it up, you can see that properly. And this is splittings off because of the 3-bond one. Because we have assigned this is 1D, and it's not enough to assign completely whether 2 bond, 3 bonds one. We require 2D experiments to do that. We have a couple of 2D experiments has been performed onto this to final assignment of this molecule. Let us go to this one experiment to identify that which is my proton, fluorine, and couplings. We have an experiment 2D called a simple COSY experiment. Okay, COSY is probably the new students just want to introducing. COSY is correlation spectroscopy. If you have a 3 bond, if a simple example, proton, proton, COSY will be done. This you have a 3 bond, bond 1, carbon, and other protons. This correlation can be get from the COSY. It's a correlation spectroscopy. But in this case, what I have done the proton fluorine COSY. Okay, so you have something like this, molecule fluorine and here a proton. If you have this kind of connections, you will get the COSY peak for that. This is a correlation spectroscopy. Okay, same thing now in this experiment. The direct dimension is the proton and indirect dimension is the fluorine. Basically, if you do it, it's based on the 3 bond couplings only. You can go through that. So here only wherever these protons are present near to the fluorines will get a peaks. Apart from that, like this is a proton over here and this proton, that coupling will not appear. Again, there are some couplings over somewhere here, it won't come up. Only wherever the fluorine is present, this is only comes up in the pictures. You can say indirect dimension peaks for the fluorine, one fluorine peak for here, one is here. You can see that. And as per the assignment, you can see that this is a fluorines for this one, this ring fluorine, and another F4 and F2. This fluorine and this fluorines one will be here, this one. Okay, and you can see the coupling, but here there is a 2 peaks over it. Is again this whether it is a H4, now it's assignment of this one cases, whether this proton, okay, this is the one cases, this is the proton cases over here, 2 assignment parts, whether this proton or this protons, it's not sure from the simple cozy experiment. Okay, it may be maybe chemical shift wise you can say that whether this is whether this proton or this proton on these 2 cases, confusions. Then when you do another advanced HMBC experiment, from that you can identify that which is the one proton H4 and H6 cases. So this kind of interesting experiments can help you for the assignment of your molecules. If you sit and properly do the assignment of the individual peaks, then you are able to identify the correlation of these whole molecules. You can identify the illustration parts.
I'm going to ask, where is this most useful? Because if you have the coupling constants, the J values, those tell you which proton is coupled with which fluorine.
Yes.
Also.
That's
So when is this experiment going to be more useful than just matching the coupling constants?
Okay.
The normal 1H and the normal 19F 1D experiments.
Okay. So when you have a simple 1D, if you have coupling constant too strong, the peak may be merges from this. So when the peaks are merging, the splitting patterns, difficult to identify whether it's a fluorine couplings or proton-proton couplings, or maybe assignment of identify the exact coupling constant, or will be difficult for you to whether it's a fluorine-proton couplings. But when you do the proton-fluorine cozy experiment with the decoupled pattern, so we'll get a separate peaks for you. So that will identify that only in this case, fluorine coupled proton only comes. Other peaks will not be vanishes everything. Suppose I have my proton with the fluorine coupled, another one proton is without fluorine coupling, it's merging like this. You know, simple 1D NMR, difficult to identify the coupling constant for this one. Now what I can do, if I do a cozy experiment, I'll get only these peaks for this. Okay, this peak will vanishes. Maybe this one, I will vanish this one, only this peak will comes up. Then I can identify, okay, this proton is coupled to the fluorines or that ring protons. So 1D will make some more complexity. Of course, 1D can give you coupling values, gives you identification of the whether proton fluorine coupled one or not coupled one. However, when you have complex structure, molecule size is big, peaks are merging up, then the cozy might help you out in these cases. So you can assign this part, and plus we have experiment called the fluorine carbon HMBC. Again, so we all know that a proton carbon HMBC, it's basically a long multi-bond correlation, long range coupling patterns, right? You generally utilize for your experiments. But you can assign an experiment for the fluorine and the carbon HMBC experiment, so that you can assign that. So if the fluorine, as I mentioned, the long range coupling is present, very strong, this fluorine can give a chain for this whole things. And same thing fluorine for this carbon and this carbon and this carbon, everything goes. And if it is so strong, this fluorine can give up to this carbon also, it can go to this. Okay, from this you can assign that. So you have, this is basically a fluorine dimension, the direct dimension observation of fluorine as like a proton, indirect dimension is a carbon one. Okay, you will get the cross peaks for all the carbons and the one fluorine cases. You can identify it. So you can make the chain identification for these cases. Okay. If you do assignment, you can easily identify these categories. Experiment is very simple. Multi-bond correlation as a proton-carbon correlation. Similar way, instead of the proton, we can go with the fluorine side to identification these cases. We can identify that proton sides over here. Okay, and the small peaks you are seeing that it is basically coupled. Again, when you do HMBC or HSQC, this works based on the 13C, not a C12. So now you have a center peak, big peak, right? That is no useful. It is completely vanished, because when you do the HMBC, all works based on 13C based one. The small satellite peak is important for you now. Okay, that will give an impact for the HMBC 2D, all 2D NMRs are that. So now this is just an example to show that how the decoupling will help you out. This is no decoupled, makes a lot of splitting patterns, and the full decoupling on the indirect dimension can the single carbon spectra. So assignment becomes much easier for using into the your characterization sites. So the next experiment also can be the proton nitrogen HMBC. Okay, so this is also not most utilized. You can use that. Now the proton, carbon, nitrogen, if you do this one, you have, this is basically nitrogen one, you have nitrogen over in the triazole groups, and again here also you have nitrogen one. Now if you do the HMBC one, this one proton is enough to give correlation to here and here this nitrogen. Similarly, this proton can correlation to this two nitrogen, and this also can give to the correlations. Now when you do this one, you can easily identify that. Now we have assignment is made over here, you can see easily identified. It's basically you have the 4, 2, 1 this ring, and this proton belongs to that, and you can make the assignment for this. Similarly for that you can do this. Let us zoom these areas. Okay, you can see that this is basically of this network nitrogens one. You can see that if you zoom that area, you can clearly identify the individual peak splittings. From that you can identify the individual peaks. Now you can see that where you have the CH2 protons over here, no, this is a protons where you have the 3 bond couplings, 1, 2, 3 bond couplings over here, and behaves it too differently. It separates. Okay, 3 CH2 1. So okay, this is a 1, 2, 3, 1. Okay, you can have these couplings one. You can see this. So this is we can make assignment. When you have a nitrogen and proton correlation, proton carbon correlations, you can pick up the experiment. On all the experiments are ready in the templates. You can make that. Of course, the coupling values little bit variations based on the literatures are available. You can input that values, and you can run this experiment for you. And these all are the universally detected or proton based or fluorine based detections. Experiment time is very less, maybe 1 hour, 2 hours, you will get a very good data of this, especially fluorine based carbon correlation experiments. Very fast acquisition can be done with these cases. So this is an interesting one, and again there is a fluorine nitrogen again. You can see that the only this ring will give a correlation, but here nothing. It is basically a direct dimension of fluorine and indirect dimension nitrogen experiment. You can get this is a correlation peaks over here, 2 nitrogen peaks can be seen. This is you can identify when you make a chemical shift chart, you can identify the chemical shift values for that. So there are interesting experiments is available in NMR for utilization for this complete structural characterization can be done in these cases. So finally I will not go into detail about all the things. Maybe you have experts, you can discuss, or maybe there are plenty of literatures available on this all individual experiment to know more about it. So one of the last, before completing that, I want to come up with this experiment. It is called the LRHSQMBC. It's one of the very recently developed, we can say. It's not so new, it's 2021 or something like that. Very interesting, it gives a very weak coupling muscle can be picked up. You can see that is the ring mentioned over here. This fluorine can contribute to the long range couplings can be seen very clearly. Very nice contours, very high sensitive can be seen that, signal to noise ratio can be seen this. You can do it for the direct dimension will be a fluorine and indirect dimension will be a carbon. Now why we preferred here it is that sometimes what happens is the coupling between this and the long range is very weak. Okay, that cannot be picked in the normal HMBC. HMBC will not give. When you have again 2 bond, 3 bond has a confusion. Plus long range will not be picked up. But LRHSQMBC uses specialized pulses, adiabatic pulses and different methods, and you can get a all correlation. Long range coupling can be seen in this LRHSQMBC, and this pulse program is again ready with your system. And you can take any modern spectrometer, this is easily available. You get more information thus. So I would like to conclude my presentation now. So I have used, this is a guide, so very nice for the fluorine NMR identification. You can go through this book and you can get a plenty informations. And in YouTube also you can get a plenty of YouTubes on that fluorine NMR. Thank you very much. Yes. Okay, if you want to take it. Yeah. If you have, I can share that also books with you.
Yeah, I think first I have already shared this with me.
Okay.
And maybe can we share this with the student with the books of copy? I think you shared this book with me. The PDF compact.
I don't know.
I think about 1 or 2 months back.
We'll talk some, yeah.
Yeah.
I don't know.
I can also share this.
I have this. Okay, I think this was a wonderful again talk where we learned about many aspects of fluorine NMR. So any questions? Yeah, we already had some discussion in between. So I think if there are no more questions, so we should thank. I think you have something.
Maybe I have one suggestion or one thought for people. You know, a lot of times in methodology, you might be able to include a fluorine atom on your substrate or as a handle to use NMR for rapid screening.
monitoring is one of the interesting talking about that. Can
So-
you please again, I missed that.
So when you do fluorine chemistry, it's easy to monitor, and your goal is to make a fluorinated compound.
Mhm.
It's easy to monitor conversion, yield, things like that. But if you're doing a methodology and it's not fluorine specific, say you're just doing a Suzuki coupling
Okay.
or some, cyclization chemistry, if you put a fluorine atom somewhere else that's not the key bond you're trying to construct, you can still use that as a handle to monitor conversion and yield quantitatively using the NMR. So, we do that sometimes. We're trying to do a certain reaction and we're trying to make a fluorinate over here on the molecule, but we might put a second fluorine atom on the far side so that we can differentiate starting material, intermediates, product A, product B. Even though we're trying to do chemistry over here, we can still track what's going on with the rest of the molecule by another fluorine atom.
Yeah, great. I think the monitoring is with the fluorine NMR is much better than the GC because you don't put your fluorinated compound on a GC.
It's not
recommended. Yeah.
You don't have to use a deuterated solvent, so you can take your reaction solvent
Solvent, yes.
straight into an NMR tube and run your experiment. It's really easy.
Yeah, so just we should thank Srinivas for coming. Okay. Thank you so much. Okay, so we take a break for lunch, and after the lunch we are starting at 2:30.
Whatever you stop and we know what's going to happen, that floating that will do T1 coupling that can happen. But is it also possible to have the two space interactions between fluorines? Because there are
He
fluorinated
was
associates.
one he was showing his paper. He has utilized the proton fluorine Gauzy experiment for the it's a Gauzy peak, it's anti-phased. You cannot make a
Okay, so post-lunch day 4. The rest of the session, we're going to subdivide into 2 subsections. So there were still some slides from the main part of the talk that I think are important enough we should go through. And then there's the tutorial. And I'm going to see how much time we have left for the tutorial. I might teach a couple of examples from there, but you'll see they're in-class problems. They're in-class problems that you don't have to be in class to do. Okay, so we can let you take them home, try them at home, and then I can give you a couple of answers tomorrow, or I can send answers by slides also later, okay? So if we cut the tutorial short, you can still do the exercises and I can still provide the answers. So let's go ahead and move forward in material. We had talked about those 2 of the 3 main mechanisms of drug metabolism, and so the first one we covered was actually on the bottom, the aromatic hydroxylation. Remember, those are reactions that proceed through the arene oxide, and we're really concerned about pi density when we look at those processes. And then the second one is the, sorry, I'm looking for my pointer. I thought I was carrying around a second ago. The second one is the aliphatic oxidation. In the aliphatic oxidation system, we're thinking about bond strengths, bond association energies as being the most important things there. Oh, well, I
remember seeing it next to your
sorry? Oh, there. Water bottles. Okay, thank you. Yeah, all right. I couldn't see it because it was right behind the water bottles. Okay, so this one involves the pi density. That's what we're predominantly thinking about. In this case, we're looking at the CH bond strength. Now we need to talk about the final 2 processes that are mechanistically somewhat similar. O, dealkylation, and N dealkylation. In these cases, we'll have a CO or CN bond attached to an alkyl group, and we'll generate a phenol. There's a subset. Some people talk about demethylation and dealkylation as 2 separate things. I think of them as the same thing. Okay, dealkylation of a methyl group, it's still dealkylation. So let's talk about the mechanism by which these occur. It's the same iron oxo species that we're thinking about. It's being catalytically active. The mechanism for O dealkylation is similar to aliphatic oxidation. The initial step involves H atom abstraction. When you do H atom abstraction, we come to an iron hydroxide, and then we generate a radical alpha to the oxygen. The only difference is that we have an oxygen before we just have a normal carbon skeleton. Okay? So you still have that H atom abstraction and the radical rebound process that forms the CO bond. But when we reform that CO bond, we now have a hemiacetal. Those hemiacetals are unstable under aqueous conditions, so they'll spontaneously decompose under aqueous conditions to generate formaldehyde. Or if you have a larger alkyl group, it would be an aldehyde with whatever the R group is. But you get an aldehyde and then your hydroxyl group. So that's how dealkylation occurs. Again, mechanistically, still H atom abstraction is the first committed step. And we're talking about H atom abstraction. What properties do you think are going to be most important for regulating H atom abstraction? We talked about in the aliphatic systems. Still think about bond association energies, BDEs. Okay, so fluorine can perturb the BDEs. Now, N dealkylation, there are multiple different mechanisms for N dealkylation. Okay. The first one is going to be exactly like we saw in the case of O dealkylation. For O dealkylation, we did an H atom abstraction first. For N dealkylation, you can still do an H atom abstraction that gives you an alpha amino radical. This radical can undergo a recombination reaction with the iron hydroxyl to generate a hemiaminal that can spontaneously decompose, again, to make it formaldehyde or some other aldehyde, depending on if there's a group attached here. And then it releases the amine. Okay. Now the body can further clear the amine better than it can the parent structure that would be alkylated. So that's one possible mechanism, and there's definitely experimental evidence in the literature to support this mechanism, but there's a second mechanism that also occurs, and it's a substrate-dependent basis, whether the dealkylation reaction occurs through the H atom abstraction or a direct oxidation of the amine. So in the second possible mechanism, instead of abstracting hydrogen, you'll do a single electron oxidation, reduce your iron by 1, and when you do this, you get a stable amine radical cation, and then a subsequent a subsequent step will generate your amino radical, and then you can continue along the same track. So in this case, we have to think about the oxidation of the amine. The oxidation potential of the substrate is going to be more important for that reactivity, not the CH bond dissociation energy. Now, fluorine can modulate either one of those properties, and we'll talk about why that is in the next series of slides. But first, let's look at bond dissociation energies for the ethers. And we have a model system in this case that has just dimethyl ether. You can see that hydrogen atom has a BDE that's reasonably weak, 96 kcal per mole. If we fluorinate on the other side of the molecule, we fluorinate over here, we increase BDE. We increase BDE because there's an inductive effect. The inductive effect pulls electron density away from the radical. Okay, so that's a destabilizing interaction. That means you have a stronger CH bond there, and you can see the delta BDE is pretty significant. We can also fluorinate alpha. When we fluorinate alpha, we also increase the BDE, and that has a different reason. We have the counteracting hyperconjugative effects and the inductive effect. The inductive effect of fluorine is always strong, it's always there. In the case of one of these types of radicals that's fluorinated at alpha to oxygen, think about what's going to be more stable. Is fluorine going to be better at donating its electrons to hyperconjugating? Or is oxygen going to be better at donating its electrons? Okay, oxygen is less electronegative. It's happier to donate its electrons into the system than the fluorine atom is. And so that minimizes or negates the hyperconjugation. The hyperconjugation that stabilizes that radical predominantly comes from oxygen. It doesn't come from fluorine. So in this system, fluorine is only doing inductively withdrawing electrons. It is not effectively hyperconjugating. The hyperconjugation is more stabilizing through the oxygen, and that's consistent across both structures. Okay. So that's what's going on in this system. The lessons are up over here. You have a destabilizing sigma inductive effect. The hyperconjugative effect does not happen through fluorine, it happens through the oxygen. So if you fluorinate alpha to the oxygen and ethers, you generally stabilize those molecules against H-atom abstraction. So this is just a series of molecules that came from my lab. These are analogs of dextromethorphan. Dextromethorphan is an FDA-approved antitussive. So you take it to stop coughs. And I might need that by the end of the week because my voice is getting worse and worse as I keep talking all week. Okay, so the parent structure has this methyl ether, and that gets dealkylated by two different processes. You can do N-dealkylation, that generates the amine. You can do O-dealkylation. When you look at the literature and the rates of these two processes, O-dealkylation seems to occur faster than the N-dealkylation. So this is a story that's heavily synthetic. The question became, how can we take the parent drug and in a short series of steps generate a variety of fluoroalkyl derivatives that would resist the dealkylation processes. The drug itself has a reasonably short half-life in vivo. It gets cleared really fast, so this is in vivo data. That's the plasma clearance rate and the half-life of the drug, and we can introduce fluorinated substituents and stabilize these molecules substantially in an animal model, improve the distribution. I don't have the distribution data here, but you do get a 10-fold increase in plasma and CNS concentrations in this series. And there are some studies, if you want to dig into this one, they're in the SI, that have isoform selective data in terms of how fast these compounds are decomposed. And it becomes clear that with 3A4 and 2D6, you retain more of the drug active in these models. In contrast, the parent structure decomposes pretty quickly. The properties, the principles, are things we already talked about. We're generally introducing fluoroalkyl groups onto a methyl ether to stabilize against that dealkylation process. Okay. So that's one example there of inhibiting an O dealkylation process using fluorine. And to discuss the N-dealkylations in more depth and how we're going to use fluorine to perturb that process, I want to come back to this figure briefly. Okay? So in this figure that you saw previously, you saw this one down here, reminder that the Michaelis-Menten. We need to think about drug association to the P450. Okay? Then we think about the catalytic process. Most of the discussion, again, revolves around the catalytic processes and mechanistically what's going on there. But you can also perturb the affinity of the drug or the dissociation of the drug from the P450, and that can have a profound effect on the metabolism. Okay. Now, for some of these P450s, they're going to have an anionic residue dangling around the active site that can recruit basic amines, another basic moiety. So if you have a charged amine, that's going to have higher affinity to the P450. It's going to recruit the P450, the active site, faster. So you're perturbing the Ka term of this equilibrium. If we attenuate the beta for N-dealkylation, the BDE is not that important. Okay? So I'll show you some data here. It's a series of derivatives for which we have just an ethyl group, and we go from the normal ethyl to the monofluoro, difluoro, trifluoroethyl. All of those are at the position that's one away. Okay? So that's this R1 group here. Recognize these are all beta substituted. They're not alpha substituted. If you have an alpha fluoroamine, the lone pair of electrons on nitrogen can push off the fluoride and make an iminium ion. Those are not stable species. So alpha fluorination of basic amines is not a good idea. Okay? So these are all beta substituted amines in the first series that's highlighted. We're just leaving the other groups as being hydrogen atoms. My group, this is in that review that I was mentioning before that's currently under, it was resubmitted a couple of days ago. So we calculated the BDEs here, and there's really no trend. And statistically, look at the delta, plus or minus 2 units there. There's no difference there in those values. They're all within a couple of kcal per mole. That's the error of the computations themselves, okay? So it really doesn't make a difference when you look there. If you look down a series, so we have difluorination of adjacent ethyl groups, same story. If you monofluorinate, difluorinate, trifluorinate, like, and again, this is actually difluorination, tetrafluorination, hexafluorination. You really don't see a change in the BDEs there, okay? So I'm trying to argue that the rules for O-dealkylation and N-dealkylation are different. So what does perturb N-dealkylation? So the second mechanism I talked about was the oxidation. In the oxidation, we can calculate, to estimate the ability of fluorine to modulate the metabolism for that mechanism, we can calculate the oxidation potentials. And that's what's been done here for a series of compounds, the same series that we saw before. You have ethyl, monofluoro, difluoro, trifluoro. The oxidation potential increases as a function of the number of fluorine atoms computationally. So if this mechanism is operant, the more fluorine atoms you put at the beta position, the more you're going to resist allowing an electron to leave. Okay, we can say that at another time. These are more resistant to single electron oxidation as you add more and more and more fluorine to the molecule. Okay? So that's a step that would affect the K-cat term. Let me pause for a second. Does that make sense why? Let me explain the background why. So if you have a cationic species and an electronegative substituent in the vicinity, the electronegative substituent is pulling electrons away from a cation. That's not good. You have electronically, there's going to be a lot of strain in that molecule. So the fluorinated compounds do not want to give up their electrons very much. Okay. And the trend holds true. I don't want to go through every example in detail. The trend, when you look at these sub-series that are built within the slide, the trend is still true. So now let's come back to the affinity term and think about how fluorination might perturb the affinity term here. In this series, we're still looking at the same types of molecules that we did before. We have the non-fluorinated, monofluorinated, difluorinated, trifluorinated ethyl groups the pKa decreases as a function of the number of fluorinated groups there. So you can see delta pKa right there. These are computational estimates of the pKa's of those. And we can actually modulate the basicity of the amine up to 5 units. So we're talking in between, about the heterocycle, and I was saying my rough estimate in my head is 4 to 5 units. And again, this is kind of where the 5-unit thing is if you have a CF3, a carbon, and then a CF3 away from an amine. So we can take an amine that's basic and fully protonated under physiological conditions. Right? The pKa here calculated 10.7 versus 7.4 pH, normal physiological conditions. It's nearly fully protonated for all practical purposes. And now we can take that amine and render it so it's neutral under physiological conditions, or at least in a 1-to-1 ratio of neutral and cationic. And when it's neutral, it's not going to have this high affinity for the P450. We perturb the association constant, decrease the metabolism. Okay? Really basic properties that can be exploited in drug discovery. Again, the trend is the same when you looked at the next series here or when you look at the final series down on the bottom. Modulation of amine basicity is one of the key, most important concepts in medchem that kind of applies in all types of settings. It perturbs metabolism, it perturbs ligand-protein interactions, and we saw it yesterday too. So let's go ahead and have a look at another molecule that I posed right at the beginning of class. We're going to go over here and look at this guy too and see what happens with the metabolism of that molecule. That's also an FDA-approved beta blocker. The beta blockers, when you can recognize them really easily by the suffix. Yeah, there's a whole bunch of them. They're really tough to say. So this is propranolol, but like there's little memes and things like that about how hard these are to say on the internet if you look for them. Okay, so this molecule undergoes a couple of different metabolic processes by 2 P450s predominantly. You get dealkylation of the isopropyl group, and then you also get aromatic hydroxylation. That was the mechanism that we saw earlier today, the first mechanism we looked at. And so this is like one of the best studies in enzymology and metabolism that I've ever seen. Yeah, there's a lot of data there. I'm going to summarize it briefly, and I'm going to use the colors to walk you through some stuff here. And on this slide, I have 3 papers cited, and this one just kind of covers one of them. We're predominantly focused on the N-dealkylation for this example. So I'm ignoring the studies on the aromatic hydroxylation and just focusing on what's going on, the formation of this metabolite right here. Okay? The big picture here is that modulating the amine basicity affects substrate recognition, not the catalytic process itself. Okay, and that's what this data is going to show us. So first, let's look at a couple of match pairs. I've highlighted the S and the R in the enantiomer differently, so blue and red. You can see the R and the S there. So if we compare these two compounds, the methyl versus the trifluoromethyl, the K-cat doesn't have a massive change. Okay, 12 versus 7 is not that big of a change for the catalytic activity. And it turns out that the catalytic process is actually a hint faster for the fluorinated version. That's the wrong thing. Like, you don't want that. So if the enzyme sees those two molecules, the methyl and the CF3, it actually metabolizes the CF3 faster in this case. Huh, okay. And the same thing is true for the R enantiomers. If you have the R enantiomer, you can see K-cat is a little bit faster for the CF3. That's not good. Fluorination, in this case, has a huge effect on the substrate recognition. And so the Km value comes out of the Michaelis-Menten kinetics. It's the equilibrium constant where you get half max rate. So if you haven't had hardcore enzymology or hardcore mechanistic enzymology yet, you're going to get to it, and it takes a lecture to kind of teach this model fully. But this correlates under some assumptions with the affinity of the drug. There's some assumptions there, but it does partially correlate with the affinity or association. Okay. And so in this series, you see a massive change in the substrate recognition as a function of pKa. So let's walk through this briefly, and instead of looking at the substrates themselves and the substructures, let's focus on comparing the pKa's with the association there, the Km value, okay? So if we have basic amines, your Km is not very good. Sorry, it is good. It has good substrate recognition. As we still have a basic amine, the substrate recognition is still pretty good there. As that amine becomes non-basic, you see the association constant get higher and higher and higher. That means the enzyme is not recognizing the substrate as well as the amine becomes basic. Less basic and neutral. Okay? So that's the key thing, the key correlation I've highlighted there in blue. As you become more and more and more, less and less and less basic, your association changes. So I've put those points there on the slide. Another key point is that it's not just the grease in the molecule. We talked about how the CF3 can improve the greasiness of the molecule, the log P of the molecule. Some P450s just love to recognize grease and metabolize grease. And in order to compare that, we can make comparable substructures that have just big, greasy moieties attached to that position that are very lipophilic and basic, and those actually, the enzyme loves those. The enzyme sees those and gets attracted really quickly. And again, it's an enzyme 2D6 that has one of those carboxylates that loves cationic amines. So that's the story here. Ultimately, I'm not going to go through the data, but you can look through, this is data for just the dealkylation. You can also look at the other oxidation processes too, and you see the same trends when you look through this data. And it takes a while to dig through it, and it's too long to teach in a class period. That's why, or like in a class where we want to talk about some other things too. So I've left that in there for you to look at. But in that case, it's also involving the oxidation occurring here. And the key thing is that the basicity of the amine still correlates with the Km value. Even though it's not dealkylation. Okay, it still correlates there. So that's a key point. I'm going to pause there. And dealkylation is pretty important. This is a common process. Other questions or walk through it clearly enough?
Right oxidation, maybe the basis of amine is altering its binding affinity to the receptor.
Yeah, so I want to come back and have this, even though it's different data, I want this figure on the slide to talk. So, right, so sometimes depending on the substrate, the moiety that's metabolized is the one that's also recruited. And that's what was going on in the deisopropylation reaction. The amine's attracted, but it's also getting metabolized. There are some other substructures for which the recruitment still occurs through a basic amine, but it's actually a moiety over here that's getting metabolized. And so you can still modulate the metabolism by modulating amine basicity, even if your site of metabolism is somewhere else on the molecule. Okay, and it's a case-by-case basis, and which P450 it is, and the shape of your drug, and the distances of the different moieties in your drug. There's so many different things that are unique to any specific example.
It is correlating, that means it is a very appropriate example.
And these types of studies at this level of rigor just aren't there.
Yeah.
For comparing the fluorinated substructures to the non-fluorinated substructures, and really a beautiful matched pair case with a lot of data to dig through. So usually you get simpler experiments like this. This is one from my group that was pretty quick, looking at how you can modulate the oxidation potential of other heteroatoms also. And so this is an example in which we're looking at oxidation of sulfur. You don't see many aliphatic thiols in drugs because they get oxidized so easily. So don't propose it unless you want it to be oxidized, okay? And so in this series of data, or in this series of matched pairs, you'll see the HH versus the difluoro substrates and the potential of the oxidant being used there. Okay. If we have the HH compound and treat it with bleach, within an hour you fully decompose the substrate. The fluorine difluoro is completely stable for all practical purposes. So you could use these to resist oxidation if you're trying to include sulfur in your molecule for some reason. And it's more stable even with stronger chemical oxidants. KMNO4, peroxide are stronger, and we still resist all oxidation with that gem difluoro substitution. And similarly, when you get to MCPBA, a little bit stronger of an oxidant, then both of them decompose and make the S oxide. Okay? So you can be creative and think about the perturbations, the physical chemical basis of those perturbations, and perhaps use them in other settings. Okay? So, maybe some of these CF2 compounds might be useful in some drug discovery campaigns. So let's see, conjugation. At the beginning, I said there were historically two phases, even though now we kind of use the names oxidation and conjugation, and fluorine can perturb conjugation also. So let me just suggest, I'll put a couple of examples out there of the processes that occur during the conjugation phase. Glucuronidation, we attach a glucuronide. All of these have some type of cofactor that's responsible for delivering the moiety. So that puts on a sugar, glutathione. We can put on sulfates. If you put a sulfate onto your molecule, that can be recognized by anionic transporters that facilitate clearance of the drugs through into the feces or through renal processes. You can conjugate amino acids. Oops, that's embarrassing. You can acetylate, and there are a couple of other examples of conjugation processes. In general, for these processes to occur, you have to have either a nucleophilic moiety on your drug or an electrophilic moiety on the drug. So if your cofactor is intrinsically electrophilic, then you need a nucleophile on your drug. You can see representative examples there. If you have a nucleophile in your cofactor, maybe that will react with some type of electrophile that is either on your drug from the beginning, but also formed from a metabolite, like the epoxides that we saw before. Those are formed in the metabolism process, and those can still react with some of these. Okay? So, our substrates are going to have reactive groups, and fluorine can modulate the electrophilicity or nucleophilicity of those types of species. So this is a series of examples, again, that come from the Meyer database. So the Meyer parameters, some people are familiar with those. Those are quantitative metrics used to estimate the nucleophilicity or electrophilicity of different groups. These are tables that you can scroll and scroll and scroll and scroll and scroll through. They have all kinds of things documented. How nucleophilic is an aryl to an alkyl or to an alcohol or to an amine or to an amide. Like you can look at these tables and estimate the relative nucleophilicity and electrophilicity. So this is like a reference or a website like every organic chemist should be aware of, and you can use it when you want. So we borrowed a couple of data points from this table just to ask the question, if you use the Meyer scale, which is useful for many purposes, how would fluorination affect the nucleophilicity of simple alcohols? And these are log units, so when we think about 4 log units, that's a 10,000-fold decrease in nucleophilicity for trifluoroethanol versus ethanol. So that's a pretty powerful effect. When you look at IPA versus HFIP, you see a similarly powerful effect there. And it also works for amines. So if you think about the nucleophilicity of amines, when you start putting on CF3 groups, the 2 position, you have isopropylamine, you convert it over to a trifluoroethylamine, you can see significant decreases in nucleophilicity. That nucleophilicity will be relevant for the phase 2 processes or the conjugated processes. Okay, so let's think about maybe a prototypical example here. This is a clinical candidate, vegocestat. This was an Alzheimer's drug that went into clinical trials. The precursor to the actual drug is shown here. You can see a primary alcohol. Primary alcohols are not typically found in drugs because phase 2 or conjugated metabolism occurs so quickly for primary alcohols. It's not a substructure you'll find very common. Okay. So in this drug discovery campaign, MetID was conducted, metabolite identification, MetID. And so in MetID studies, the two aliphatic groups, the ethyl groups that are part of this pentyl moiety, were oxidized. And then you also have the conjugated metabolism, glucuronidation, occurring over here on the primary hydroxyl group. Now these processes led to quick metabolism using the microsomes. That was that ER-based model that I talked about, where you strip the ER out, get little get samples that had the P450s and use that. That's a microsome, and then you use that as the model. Nonetheless, you could dose a high concentration of the drug into this transgenic mouse model and see reduction of A beta plaques after some time. The selectivity versus Notch, that's another protease that they're trying to avoid. Okay, so that's a selectivity factor down here for the gamma secretase versus Notch. So we need to solve those problems. The team did an analysis and recognized that we can probably try to solve the metabolism over here. Not quite sure what we're going to do with this yet. So in order to solve that metabolic process, what do you think they did? And we know what this course is about, so you know, it was a little bit of a question that I hope everybody would guess the answer to. Let's fluorinate and maybe methyl to CF3. This is a greasy pocket. Maybe it tolerates a little bit larger of a substituent. So hey, let's make it. It's symmetrical. It's probably easy to make this fragment and then conjugate it onto our amine. So in this case, there definitely was an improvement in the half-lives in the microsomes. They could dose the drug at lower concentrations and still get the same efficacy and improve selectivity. That's great. That's great data right there. It turns out that there was still a metabolic issue in the oxidation phase. Instead of oxidizing the terminal position, the P450s decided we're just going to oxidize vicinally right next to it. And you still had the issue with glucuronidation of the primary hydroxyl group. So even though we're getting better, there's still some issues to solve. So now the question is, what are you going to do? How are you going to solve this? You have two metabolic processes. You have the hydroxylation and then the conjugation process. We need to modulate, CH abstraction processes over here and block somehow over here, and we need to reduce the nucleophilicity of the alcohol. So it's a really clever solution. Maybe we can truncate it. If we truncate it and we have those CF3 groups, we still have quite a bit of grease, quite a bit of lipophilic character over here in this region. But we're also going to move the dipole imparted by the CF3 groups. We're going to bring that dipole closer to the hydroxyl group. And then you're going to decrease the nucleophilicity of the hydroxyl group. And maybe we can decrease the conjugative metabolism that way. So the strategy here was to remove the CH2 and the CH2. Now we have the hexafluoroisopropyl moiety introduced into the drug here. And ultimately that leads to a compound that has better half-lives and microsomes. You get better efficacy at the same dosing, good selectivity versus the Notch protein. But the concept hopefully makes sense here. Here, the dipoles from the CF3 groups are a little bit further away. They don't influence the nucleophilicity of the hydroxyl group as much as if you truncate it a little bit. Okay, so you think about the organic mechanism of what's going on, and then think about how fluorine can perturb the basic properties that are important for that mechanism, and that's what's going on here. Okay, so for purposes of right now and the rest of the class, there's another example that I'm not going to talk through because I do want to finish up and give you some suggestions for the tutorial part, but this is a really nice, beautiful study that's reasonably new. So the tutorial, okay? The tutorial has a series of slides that look kind of like this. So I think that the homework for the evening is going to take these structures and with what we've learned in general, just what do you think the metabolites are? Based on the metabolic processes we discussed, what are the most likely things to happen for these drugs? So you have one there. You have one there. That's a kinase inhibitor. The first one is an antibiotic, linezolid. You have a kinase inhibitor. We have a CNS therapeutic. This one over here is one that you already thought about. Okay, so I'm going to talk through that one in just a couple of minutes. So that one was one of the ones I put up on the slide right at the beginning. So you've thought about this molecule for a bit. Okay, and so it turns out that this molecule that ultimately became a drug has a couple of different sites of, let me get over the other, there we go, has a couple of different sites that are metabolized. So you have electron-rich aromatic rings, so that can get oxidized. The methyl aryl ether moieties undergo O dealkylation, O demethylation. We saw that mechanism already. I don't know who thought that would happen when you saw the compounds initially, but now you know. And then there's also aliphatic oxidation, specifically benzylic oxidation. I had indicated a couple of times that the benzylic position is particularly susceptible to oxidation. So this drug could be used in vivo. You can see the dose needed for efficacy here. It turns out that the MedChem team independently synthesized some of the different metabolites and identified if they're good, like are those metabolites actually active, or are those metabolites inactive? And it turns out that some of the changes increased activity, some of the changes decreased activity. So when you got the benzylic hydroxylation and the demethylation here to make the phenol, those actually activated the molecule more, but the demethylation here and the oxidation here to make the phenol deactivated the molecule. Okay, so what would the compounds be that you would start to make then? Well, this team decided, let's go ahead and pre-install the hydroxyl groups that increase activity. So the ultimate drug had a benzyl alcohol and a phenol included because those are active metabolites. Let's go ahead and put those in right from the start, and then let's block the metabolism at the other sites using fluorinated substituents. This ultimately led to the drug azetinib that requires a pretty low dose. Okay, so I think it's good to think about, well, are all metabolites bad in a discovery campaign? This team said, you know what, some of the metabolites are actually good, and we should use that to design the next series of compounds. Okay, so you have your homework, you have some of those other structures to work on, and maybe in the first couple of minutes I can show you some of the metabolites, and we have a quick discussion about that. Other than that, I'm going to stop and turn over the class to our next speaker, and we will do a quick change and get going in just a couple minutes, right?
editorial board member.
Yeah, so he, but he, I think
Thank you very much, Deepak. Thank you. It's my great pleasure to share the stage with well-known chemist Professor Altman. First of all, let me thank Professor Deepak for the kind invitation. It's my pleasure to be part of this prestigious program. My title is quite a bit unusual to what I do actually. So, in order to fit myself to this program, I had to reshape the theme of my talk. As you see, metal-free strategies to synthesize small organic molecule, including some fluorinated compounds. You can see eventually during my talk, we hardly make few compounds substituted somewhere with fluorine. Okay, I'm not a fluorine chemist, I should admit. I'm definitely nowhere comparison to Professor Altman. Otherwise, let me talk to you how we entered the metal-free scenario as of organic synthesis is concerned, and what kind of molecules that we synthesized, although we didn't explore anything about the medicinal chemistry aspects of this. Probably some of you are more knowledgeable to guide me further, if at all something interesting that I'm going to talk about. Let me start my talk by showcasing what we do at IISER Mohali nowadays. Earlier we used to have a different research area, but nowadays we have broadly two research areas to work on. One is the catalysis by phosphines. Apologies for this pointer, it does not necessarily show what I would like to point effectively, but go with me that we work on phosphine chemistry. Indeed, I'll start my discussion surrounding this phosphine chemistry, how we entered these cascade transformations promoted by sulforylates. This is a new research area, came out of nowhere actually. You will see how we entered this field, but our intention always is to create molecules for biological sake or for applications in materials chemistry. The background to the metal-free chemistry that came out of our lab is a simple transformation that we all know of. Any organic chemist must be able to realize what is this reaction, a Morita-Belli-Silman reaction, which is typically promoted by tertiary phosphines or amines. It involves a carbon-carbon bond formation leading to such densely functionalized molecules starting from the readily available compounds such as activated olefins and carbonyl compounds such as aldehydes or ketones. It's reported quite some time ago, almost I should say, as you see the reported publication, early 1970s. What is interesting as of this particular reaction, indeed I should say how my teaching actually helped in coming up with this question. After teaching this Belli-Silman chemistry one day in a class while I was walking backwards, I realized that how and why always the chemistry is shown only with beta unsubstituted systems. What happens or what happened once you introduce substitution at the beta position to these activated olefins? That was a simple question I asked myself. Once I digged literature, I realized that this is a very common substrates. The one that I showed on the top equation, beta unsubstituted systems. Once you start introducing substitution, say let us say mono substituted one, very few examples, very few, and this is not general even now, these reactions are not even general. Once you have the beta position fully substituted, there are hardly any examples. Indeed, there are no efforts, especially in intermolecular sense, leading to such compounds. This is something that I realized. Okay, that means that once you have substitution introduced at the beta position, this reaction becomes more and more sluggish, and of course it reaches a stage that reaction does not work when it is beta disubstituted. why, of course, of course, I try to convince myself probably this is not something worth thinking, because it's obviously because of steric reasons. Once you have beta disubstituents, that this incoming nucleophile cannot initiate the process leading to the enolate formation and subsequent transformation. Then I also found that the same reaction in intramolecular sense was also reported with beta unsubstituted variation. As you see here, such reactions leading to the cycloalkenes were also pursued with no substitution at the beta position. Of course, this is a beta monosubstituted by virtue of being intramolecular. But otherwise, I did not find any cases where the beta position, even in intramolecular sense, were substituted here, leading to the respective products. So with this background, we came up with this design. Actually, I could have spared some time to explain what is the origin of this particular substrate design, because of the paucity of time, I will skip that part. But we came up with this design. If you see carefully, what the design effectively involves is the tethering of both the electrophiles. Of course, both are electrophiles from reaction point of view. For a phosphine to react, this is an electrophile. Once enolate forms, this is electrophile. So these electrophiles situated ortho to each other, and they also assume what is so called synergism or mutual cooperativity. Okay. Once this is more electrophilic, for example, your first step where your phosphine or amine reacts, that can be faster, and once this is electrophilic, obviously that intramolecular aldol type reaction also will be faster, leading to the product. That was what we assumed for the driving forces behind this substrate design. Of course, eventually that is the product we realize, if at all the reaction is successful. And once it is intramolecular, unlike an intermolecular reaction, you all realize that it is entropy favored, unlike as I was saying, in intramolecular process. With this in mind, as you see, we initially went on with the monosubstituted systems. This is a typical methodology work. You may not really enjoy the other part that I am talking about, but once you have a beta monosubstituted system, the reaction works quite well, as you see, leading to variety of cyclopentane fused arenes and heteroarenes. And what especially encouraged us as part of this initial work was those highlighted in blue. Those are the substrates, where where electron donating groups are substituted on some of the other component of the substrate, either it is in the arene backbone or on the enone component. Despite that, this reaction, as you see, works quite quick, no longer than 30 minutes that it requires, and of course highly stereoselectively, as you see the results displayed here. That gave us sufficient confidence, thinking that probably if at all the monosubstituted substrate giving you the product in such quick time, probably once you go forward to a beta disubstituted system, this reaction should give you the product indeed that can also establish a reaction leading to the first beta Belli-Silman reaction of beta disubstituted systems. Indeed, that is what happened. As you see here, we could amass a large number of large number of substrates where cyclopentane fused arenes, heteroarenes can be generated, but more importantly, as you see here, all are beta disubstituted systems. These are only first examples where Belli-Silman reaction was accomplished with beta disubstituents. You can also generate, as you see here, a quaternary carbon. You see last three cases are where quaternary carbon can be generated, tetrasubstituted carbon can be generated, provided you start with ketones. Okay. One obvious advantage with Belli-Silman chemistry is that it generates one stereocenter, giving you the opportunity to pursue a chiral variation. Indeed, we spent quite a bit of time establishing the chiral variant. Ultimately, we were successful with this particular bifunctional catalyst where phosphine is situated here and a thiourea moiety on the other side. This reaction, for your information, provides the EE or NHA excess, as you see in these cases, only in HF5P solvent, hexafluoroisopropanol. Probably that fits me to this audience, that a fluorinated solvent, hexafluoroisopropanol, only gives you enantioinduction in these cases. Okay? So, no other solvent. We spent almost 6 to 8 months exploring different combinations because we did not want to publish this work without developing a chiral variant. We pursued so many combinations, so many catalyst solvent combinations, eventually we realized that only HFIP induces chirality into the product, and indeed this was the working model, although this model which is on the top right does not incorporate the role of HFIP, but eventually with the help of my colleague Dr. Balnarayan, we actually worked out a computational model which explains the role of HFIP in this transformation. If you see now what happens, this is the one that anchors substrate and the catalyst in a fashion that is shown here, forming this supramolecular assembly, and you can see that HFIP actually activates the substrate in this fashion that is shown here, and it eventually after the aldol cyclization transfers the proton, and the resulting alkoxide is actually responsible for the deprotonation, which is in the MBH context a rate determining step, and that promotes the elimination of phosphine and regeneration of the catalyst, and eventually the formation of the product. This also fits in, of course, this is a very short summary of the whole work just for the sake of chemists, but one can go through this paper and realize how detailed we worked, and that fits in the observed enantiomer selection in this particular process. Okay, having this as a background, we actually, I am just summarizing the work in the whole phosphine chemistry. We eventually went on to developing reductive aldol reaction promoted by phosphines, vinylogous aldol reaction. This is with activated alkenes on the left side. We also pursued intramolecular hydroalkylation chemistry using activated alkynes, as you see on the left, on the right, sorry, and then hydroacylation reactions leading to such products, and oxyamination reaction, as you see. So a couple of other reactions we developed afterwards which are not captured here, but this is a summary of our contribution to phosphine chemistry. Okay, at this point we asked a simple question. This actually changed the course of the recent research in our lab. We asked a simple question based on the work that I just described, this Bailey-Silman chemistry. We asked a question, what can happen if I replace the double bond with a cyclopropane? Okay, one can understand that reactivity obviously won't be the same. While phosphines undergo a Michael addition followed by aldol cyclization leading to such products, which is effectively the Bailey-Silman products, the same won't be applicable in this case, because now phosphines have to be undergoing a homoconjugate addition, and that resultant enolate we are not very sure whether that they cyclize, or we are also at that point when we ask this question not sure what can be the fate of these substrates under the conditions envisioned. There is a simple logic, and the logic is that the double bonds or the cyclopropanes are considered double bond equivalents. That is the simple logic. Okay, most of the reactions exhibited by double bonds also exhibit as cyclopropanes. Okay, so that's the reason a comparison that is set between olefins and cyclopropanes. Okay, once we asked the question, we looked up what is known as of the transformations of cyclopropanes under Lewis basic conditions. As I was just telling you, phosphines are Lewis bases. What was known very interestingly is that the chemistry of donor acceptor cyclopropanes are the vinyl cyclopropanes, and the resulting chemistry originating from these deuterionic intermediates is very well captured. In fact, you can see the review that is here and the representative paper cited at the bottom. This is very well known under Lewis basic setup. What is less known was the reactions promoted by Lewis bases and the gem deactivated cyclopropanes. Even it's so very less pursued. Even that much also is the contribution of Danishevsky way back in 1975, where he reported amine promoted ring opening cyclizations of cyclopropanes. But what is scarcely pursued was this particular case where monoactivated cyclopropanes and Lewis basic conditions leading to such deuterionic compounds and their subsequent transformations. Hardly known, and indeed we came across only one example in the literature, that is what is on the screen. Okay. In this case, if you see carefully, reported by Christoph and co-workers in 1987, phosphines react with the monoactivated cyclopropanes under the conditions shown here, form the products what are known as phosphonium salts. How this works? Phosphines undergo, as I was talking to you, homoconjugate addition, and the resulting enolate was quickly quenched by HBr, and that's what leads to what you see as phosphonium salts. What we thought, what about trapping, or is it possible to trap this intermediate? Okay, rather than supplying HBr kind of a agent, what if I supply a reactant in the form of this XY, so that it potentially may undergo a 3+2 cycloaddition or a 3+2 equivalent leading to 5-membered carbocycles or heterocycles. Okay. So, this is also the reason why we came up with the design that is shown in the last slide. So, eventually if you now combine the concept that is shown here and apply to the substrate that I was talking about, if you see this now, the cyclopropyl ketone having this aldehyde, which is effectively the same as what I showed in the last slide, under the influence of phosphine, which is effectively what is shown by Christoph and co-workers, you can see that this particular fragment is borrowed from here, and of course this is our design. Now it can undergo a cyclization as shown by these arrows, and they can deliver product shown there. Okay. This is when phosphines react from the R substituted carbon. Of course, it need not necessarily happen that way. The phosphines also can react or ring open the cyclopropanes from less substituted carbon, and that also can lead to similar products as you see in here. Of course, is a regioisomer to what you see earlier. Okay. But we are hopeful that because of precedence by Christoph and applying to our system, we are hopeful that we will get one or both of these products. Although you can understand that these are quite harsh conditions. I mean, this uses, as you see here, HBr, chloroform, 120 degrees seal tube conditions, quite harsh, but initially of course we never intended to go into that domain, but we wanted to see what can happen. Obviously it requires preparation of the desired compound. We wanted to prepare this compound so that we can execute the hypothesis that I have so far talked about. For this, what my student Uttam did was to take this compound, as you see here, the enone appended to that aldehyde, and he thought that the Korachekowski process would give him this one. Obviously, if at all you are familiar, I could have put up a Korachekowski reaction also here for the sake of students, but because time didn't permit, I couldn't do that. But if at all you are familiar with the Korachekowski process, it need not necessarily give you cyclopropane. It can also give you an epoxide onto this carbonyl. And I asked him, why did you do this reaction? So he said, okay, fine, just to evaluate your proposal, I wanted to see, even if I get less yield of it, to evaluate the the hypothesis, even if I get less yield of it. But eventually what happened was that we isolated this compound. Okay. You can see that there is no correlation between what we expected versus what we isolated. The process we called as an interrupted Korachekowski reaction eventually, but how this works is this way. The sulfoxylenimylate that is generated under these conditions undergoes 1,2 addition, and the alkoxide now exchanges proton, and the resultant ylide promotes intramolecular Michael addition, and the resultant enolate displaces sulfoxide DMSO, giving you the product as you see here. From nowhere, all of a sudden you see a 4 stereo center getting generated, and a compound that is otherwise difficult to access through traditional synthetic chemistry. And this was obtained in a 5:1 diastereomic ratio and excellent yield. Of course, this structure as such we could able to assign even before X-ray arrived, but that confirmed eventually the relative stereochemistry. This is the scope. This is something that any organic chemist does to satisfy the reviewers. Right? You can see a variety of groups who are manipulated across the substrate and achieved complexity. This is one fluorinated compound we made, so which I will talk to you later. Yeah, here, yeah, that's the one. Thank you. Yeah, because why I'm pointing out is this spectrum I'm going to show later. Anyway, this is what happened with enone appended to aldehyde. Obviously, as part of exploring the scope, we also checked the reactivity of enones appended to ketones under the same reaction conditions, you see that an entirely different product we achieved. It's now a spirocyclopropane. How this is obtained? Unlike a 1,2 addition that occurred in case of enone aldehydes, in this case, because now that these are ketones which are less reactive, probably that the sulfoxonium ylide preferred a Michael addition, and of course a subsequent intramolecular aldol setting up this particular zwitterionic intermediate, and 1,3 proton shift leading to the enolate that is shown on the right. That enolate now promotes the elimination of DMSO, setting up the spirocyclopropane. Again, here also we have shown reasonable diversity through different example, only representative examples I am showing here. This concept we eventually applied in desymmetrization also, as you see here. What you saw was enone aldehydes, then enone ketones, and the other possibility is to have bis enones. Once you have bis enones, 2 types of bis enones possible, both are symmetric. This is the context of another publication and another work. Here also you get 2 different types of products. If you see this bis enones where the double bonds are internal, you get a cyclopropane fused indanes. On the other hand, once you have the other substrate, you now see a spirocyclopropane coming out. So just to summarize up to here, this is what I showed you so far. You can see that different products are obtained with different substrates, effectively under the same condition. Reagent is the same, but different products are obtained. While we were searching, because we identified, obviously we realized that this is very interesting transformation. If at all we can expand the scope further, this would be more interesting to the community, was our intention. And while we were searching for few other electrophiles, we thought probably a pyridinium salt can be a good substitute. And however, we are not sure whether this reaction works under these conditions, because we are also not sure of the reactions between pyridinium salts and sulfoxonium ylides, because we don't want a reaction happening between the sulfoxonium ylides and pyridinium salts straight away. We want obviously the sulfoxonium interact with the enone first, and then the pyridinium should be reacting. But there was no precedence of a reaction between sulfoxonium salts and the pyridinium salts. But we went ahead, we prepared the compound as shown there, and subjected to the same reaction conditions, you can see what was obtained. We obtained these 2 compounds in 3:1 diastereomeric ratio, and both were isolated. Indeed, both were crystalline. We could readily establish the relative stereochemistry. What is more striking about it, it is not just about creating 3 stereocenters. 2 of them are spirocenters, all carbon quaternary spirocenters, vicinal spirocenters. Okay, in synthetic chemistry, usually you see several methods for the creation of spirocenters, but not vicinal spirocenters. This is quite rare example to that extent. Okay. Otherwise, this also represents an undescribed class of a scaffold. The scope was quite good, as you see here. I don't spend much time. Here also we have one substrate with a CF3 there. Otherwise, what is more interesting is the last one for me personally, because it now creates 3 stereocenters and 3 quaternary carbons contiguous. Okay, this is something that can be manipulated by introducing another substitution next to this R1. I mean to say, if at all you start with a beta disubstituted enone there, that translates to this blue carbon where you have now both R1, R2 substituted. You can now manipulate however you want. If it is a cyclic, that could have potentially been another spirocenter. But that's how we demonstrated the scope. You can see that all the products were obtained in, of course, good yields, moderate diastereo selection. Once we explored pyridinium salts, then we went on to obviously the relative of that is the quinolinium salts. Obviously, we expected similar products with quinolinium salts. You can see what happened there. Once we change to quinolinium salts, you can see entirely a different product. Okay, now you have to actually search for the cyclopropane. Where is it? It's such embedded deep in the product, as you see here, and all of a sudden you can see that you generated almost 6 to 7 stereocenters. It is even more if you want to include sulfur also as a stereocenter. But here also you can see the scope is quite broad, and of course here I'm looking for, yeah, there is some fluorine compound here. Okay, and And what is important in this case is, unlike pyridinium salts which we obtained in diastereomer as diastereomers, here all these products, despite creating up to 6 to 7 stereocenters, these compounds were isolated as single isomers. Okay, only of course this is an isomer because of the methyl group that we brought in from this alpha substitution that was responsible for the DR. Otherwise, everyone else are single isomers. Okay, this is a mechanism. I will be very quick. Sulfoxylamylates in the case of pyridinium salts undergo 1,4 addition, and the enolate now undergoes C4 cyclization, setting up the first spirocenter. Now the enol promoted displacement of DMSO sets up the second spirocenter and the third stereocenter. On the other hand, when we have the quinolinium salt, the mechanism diverges. As you see here, the enolate now exchanges proton with this sulfoxonium, forming this halide that now undergoes C4 cyclization, setting up the spirocenter and forming this 7-membered ring. Now enamine promoted displacement of DMSO, leading to the creation of this cyclopropane, and DMSO interestingly re-enters the system in this fashion, and that is how you get the product as a single isomer. Okay, something I wanted to share here is about a folding strategy. What is a folding strategy? Okay, what you have seen so far is I am only changing the substrates. I am getting different products in different cases effectively under the same reaction condition, right. So, this is what is called as a folding strategy of diversity oriented synthesis. This is one variant of diversity oriented synthesis. What Schreiber defines this as a DOS strategy that converts a collection of substrates with pre-installed skeletal information into products having distinct molecular frameworks by employing common set of reaction conditions. If you read this definition, it exactly fits the observations that we made, or the kind of results that I have so far shared with you. What I will do is I will share with you 2 more examples of this so-called folding strategy that came out of our lab, and I will lead you to conclusion. This is one. If you see carefully the top substrate, the R1 is at the beta position, and you saw the product that is formed. Okay. Please pay attention to the substrate that is mentioned in the bottom equation. The R1 effectively is now at the alpha position, right. Rest are all same. You see the difference between the top and the bottom substrates. Okay. Only the difference is the R1, the position of R1. Of course, reaction conditions are same, but you see the product distribution. Okay. This is very different from whatever that was observed in the earlier case. Okay. This is the context of another work, and I will be very brief with this, the mechanism. Now sulfoxonium halide undergoes in this particular case Michael addition, setting up the zwitterionic species 1,5 proton transfer, forming this halide that is now responsible for the intramolecular aldol cyclization, and the resultant alkoxide promoted displacement of DMSO gives these 2 products in, of course, diastereomer ratio. The ratio was not quite healthy, but good enough for a publication. That is enough for us, okay, at least at this point. You can see the scope of this work, multiple stereocenters. Otherwise, if at all you want to synthesize this kind of compounds using traditional synthetic chemistry, it definitely requires multi-step synthesis. But this is something, except that you prepare the starting compound, in one step everything is assembled in this fashion. You can even create or introduce 2 contiguous quaternary carbons, provided you manipulate the substrate as you see here, and this is some synthetic elaborations taking this compound. You can take it to different types of derivatives, and needless to say that hydrofluorinones are very much prevalent in several bioactive molecules. Okay, this is another case. As I said, this is the second case. I will conclude as of the discussion surrounding the folding strategy. This work I just described, right. You saw that the quinolinium salts appended to this enone gave the substrate, right. This is the context of our earlier work. When we questioned what can happen with an enone in place of an enone, okay, for your information, the Korsakoffsky process works very well with enones or activated olefins leading to cyclopropanes, but that does not happen with activated alkynes. If at all you take activated alkyne and treat with Korsakoffsky reagent, you do not get a cyclopropane. Even if you get it, it is transient first, because it generates cyclopropenes or activated cyclopropenes, not known in the literature. Okay. So, with that background, of course, we are aware of it, but reaction of sulfoxylamide with activated alkynes will lead to gamma sulfoxonium enones. That's a different work altogether, which is known, but we question what can happen, and you see the product that we obtain out of this. Okay, completely unexpected. It took time for us to realize what happened here. Until the crystal structure arrived, we were unaware of the outcome of this. Okay, this is the scope of the work. You can see such intricate scaffolds you can create from nowhere, from starting from a flat molecule. You have been listening to Professor Altman's lecture. As such, this institute is very well known for the drug discovery and related science. You know how skeletal diversity makes sense in terms of drug discovery. Okay, you can see the kind of skeletons that you create from flat molecules, such as what you see there. All of a sudden, you create sp3 rich systems, and this is the mechanism. Now, in this case, sulfoxylamide undergoes 1,4 addition, and the enolate or elinolate now undergoes C4 cyclization, setting up the spirocenter. Enamine promoted SN2 prime type displacement of DMSO now sets up the cyclopropane, and what we believe is that intramolecular aldolene type cyclization then provides the product. Okay. So, further efforts, further designs are ongoing, and we actually are witnessing some great chemistry coming out of it. Okay, let me come back to this question. All of you remember this one now? We deviated to sulfoxonium chemistry. I showed you how we entered the sulfoxonium chemistry accidentally. But coming back to our original question, the cyclopropyl ketoaldehydes, we now prepared by protecting this aldehyde. Earlier, you remember, we didn't protect the aldehyde, and you saw what happened. Now we protected the aldehyde and prepared purposefully this cyclopropyl ketoaldehyde, subjected to phosphine and DMSO heating. We expected this product. You remember this hypothesis? We expected this, but we actually got this indinone. What was more surprising to us was this: it didn't actually require phosphine. Out of some control experiments when we did, we realized that DMSO alone can facilitate this transformation. More surprising thing is that it's not limited to this substrate. You can see, I'm only summarizing due to the lack of time. You can see that with aldehydes, when the FG, what I'm trying to say is, when this functional group is aldehyde, this is the product you obtain, that is what is shown there. When this functional group is a ketone, you get alpha styryl indinones. When this functional group is in enone, you get to these fluorinones. Okay? That is the scope of this work, but the question remains, how about phosphines promoting ring opening transformations of cyclopropyl ketones? Can this be achieved? This is, again, I am summarizing in one slide. This could be achieved in this fashion. Against aldehyde that I shown, if at all you have this enone in place of what I showed as in the earlier case aldehyde, you actually can access tetrahydrofluorinones. This actually represents the first, at least to our knowledge, first Lewis base promoted ring opening transformations of activated cyclopropanes. Okay? Lewis acid promoted transformations of cyclopropanes are quite well known, widely known, not just Lewis acid, even bronzed acid, but this is Lewis base promoted, that is in the form of a phosphine. Although this is an unintended result, because we didn't plan this obviously, we wanted to see what happens, but we got after the ring opening transformation of cyclopropane, proton transfer gave this ylide, intramolecular Wittig reaction gave this tetrahydrofluorinones. Okay? That is what it is. This is very briefly. Again, I'm not taking much of your time, just to showcase the scope, and much more was done, of course, in the context of that publication. But this is to conclude what I'm talking about. We asked this question, all of you remember, we asked this question, what can happen with monoactivated cyclopropanes appended to aldehydes? Can we get this product? And you saw the story surrounding this particular question. And achieved, this is what we achieved so far. What we achieved, just as I shown, a cyclopropyl ketone appended to enone giving tetrahydrofluorinones. Okay? This is the latest work unpublished, still in progress. We indeed can obtain cyclopropyl ketoaldehydes giving you this product, which is what was originally hypothesized, but a slight variation in the design. If you see here, now this is no longer a monoactivated cyclopropane, is a geminally diactivated cyclopropane. So, so far that's what I mentioned, not achieved so far is the comment with monoactivated cyclopropane aldehydes. We could not yet transform them to the kind of products that we were expecting, but so far we could achieve to the products that are here, okay, provided you have an additional withdrawing group, otherwise additional activator comprising to geminally deactivated cyclopropanes. Okay. So, this is slide I wanted to impress Professor Altman. I introduced this slide. I know Professor Altman worked on decarboxylative alylation reactions using palladium. Of course, he is a versatile chemist. He has worked in other fields also, but this is something, a closed chapter in our lab. Just to summarize, we developed palladium catalyzed intramolecular aldolene cyclization reactions leading to these cyclopentadienes, and you can we also developed Nazaro type cyclization leading to such structures. We made some small natural products within that context, and of course this is one natural product. Of course, these are materially interesting. This is benzonylation reactions we developed, and using the geminally disubstituted acetates, we could actually achieve formation of chromines and small natural products in that context. Also, we almost stopped working in this field. One last work is pending just to culminate our studies in this field, but otherwise very brief. I will take only 5 more minutes, okay, just to talk about some fluorine chemistry. It's a very important nucleus in NMR spectroscopy because of its, as I mentioned, receptivity and large chemical shift dispersion, even much better than proton NMR, for example, or proton or 1H NMR. Okay. The abundance is 100% F19 NMR, 100%. It has a nucleus spin of half, which makes it responsible for its coupling with other nuclei. Right? All of you must be probably by now aware of this. And the kind of spectra I am going to show in the next few slides are recorded in a 400 MHz NMR, indicating to you that the field strength is 376. Okay. This is something based on certain calculation which you can arrive at this number based on the abundance and the field strength. Okay. This is one compound, and just as we record nowadays NMR decoupled. For example, C13 NMR, they are primarily decoupled from protons, and to simplify. Okay. What you can see in this molecule I described already. Okay. What is important here, of course, this is also a decoupled spectrum, decoupled from, proton decoupled F19 NMR spectrum. Okay. If you see here, this particular doublet like, these look like two singlets, but this is actually a doublet. What is this doublet responsible? This carbon, now this fluorine or F19 here is responsible for splitting this, and this is the doublet that is responsible for that. And whatever the J value that you calculate in proton NMR, you also have to measure here, but you have to multiply by the 376 factor, right? So that you arrive at the J value. And you can also see this is also one, fluorine is so interesting. I don't need to tell in front of Professor Altman, I should not tell more of fluorine, but fluorine is so interesting. It literally can affect everything that it is connected, especially in aromatic ring. It can literally influence all the 6 carbons of the aromatic ring. In some cases, you will see even it goes beyond that also. Okay, that depends on substrate to substrate, and you will see that all 6 are here. Actually, 1, 2, there is 3, 4 here. Here 4, 3, 4, 5, 6. Okay, followed, right? 1, 2, 3, 4, 5, 6. Okay, these are all, of course, I am not showing you the zoomed portion of it, but these are all because of the CF coupling. Okay, this is the respective F19 NMR as you see here, just as proton NMR. In proton NMR, we take proton or 1H as the reference. In this F19 as the reference we take, and you can see that this is effectively representing this fluorine, right? You can see the chemical shift -100. -100 is nothing in fluorine NMR. It can go up to 800 also, depending on the scenario. Okay, this one, and this is another molecule I already described. Here also you can see that this fluorine has created the doublet here. You can see the kind of course these are not two peaks. Okay, you need to be careful in interpreting your NMR. When you are writing the data, you should not write them as two peaks, okay, especially when you have fluorine around. Yeah, and you have two, this is 1, 2, 3, 4 here, 5, 6. Okay, 6 carbons coming from the aromatic. Okay, and indeed what we saw a slight influence on this carbon. This carbon is effectively this carbon, the OH connected carbon, slightly influenced by of the range of 1 hertz. Okay, so that much influence, it has influenced up to the benzylic carbon. Please correct me if I am wrong, but we believe that it's because of the fluorine coupling. And then this is the respective F19 NMR. And this compound already showed you so far whatever are shown, two structures are with CF bond. Now it is CF3. Okay, CF3, because this is see, for example, if you record CH3, if you don't record decoupled, okay, CH3 also will appear as a quartet in a coupled, proton coupled C13 NMR. I hope you are following what I mean. If only you will see that CH3 as a singlet only when you decouple the proton, right? So here now CF3, okay, CF3 now will appear as a quartet, okay, as a quartet in NMR which is embedded somewhere here. Okay, I could not identify through the zoomed variant. But otherwise, the fluorine also influences other carbons coming out of this particular presence. Okay, here you can see that while we saw F19 of CF at -100, a CF3 now I mean fluorines on CF3 appear at -62 in this particular context. Okay, similarly, we can talk about several other fluorine containing compounds. But I thought I should talk as less as possible as of fluorine chemistry, especially in his presence. So I thought I should conclude there. I thank my students for their contributions and funding agencies for their support over the period. Thank you very much.
Thank you. I think we might have witnessed like kind of, because in India very few labs are actually working on a single selective synthesis and making such like chiral molecules.
I hope I was on time. Sorry.
Yeah.
Okay, it's
So,
4 5.
any questions? Yeah.
Yeah.
Just on slide there is a atomable phosphine base on the less substituted carbon of cyclopropyl in hypothesis.
Right.
So is that possible it can attach to that carbon because the electronegativity difference by electron withdrawing group and electron donating group is more, but it can be attached to less substituted carbon.
Yeah. No, that was.
Any evidence or
No, there is no evidence, obviously. So it was only an expectation. See, once you have a cyclopropane, so there is a possibility. For example, I have. Okay, if I have cyclopropane like this, you see that this bond is activated by the presence of this ketone. This bond also equally activated by this ketone. That's why when we hypothesized the nucleophile attacks from this way or this way. You got right? That's the origin of that. Other than that, we have no idea, because phosphine promoted ring opening transformations as cyclopropanes, perhaps, at least I should say, first we reported.
if it is like donor acceptor.
That is different. That is very well known. Donor acceptors, yeah, in fact, I told you about that, right? So donor acceptor systems are very well known. Okay, but we are, see, if I had to deal with donor acceptor systems, we would not have entered this field, because that is so well explored. Okay, as you see here, these two are quite well explored. As I was mentioning, indeed, there are reviews on that topic also. These are also reasonably well known, not as much explored as this topic. This is something, as I was telling, in this context, only one report was known, that is this. Monoactivated cyclopropane ring opening transformation. This is the only report to our knowledge.
Hypothesis you have shown one
Ah,
This
this
one.
one. Yeah, yeah.
Here is that first thing attached to the less substituted carbon.
This one.
Red one.
Okay.
Is that possible?
That's what I'm showing here. So probably you are confused because there is no R there. But same. You see, if I put R now, you will see. That's what it is. Okay, because these two bonds are same for a cyclopropane, same for the ketone. Activation can be similar in both, but one bond may be more activated than the other by the presence of this R group, nature of that R group. Yeah. Yeah, you're right. If it is withdrawing, then probably this bond is more prone to cleave. Yeah, that's what it is. Yeah. Yes, please.
In your slides, there were so many stable centers.
Right.
And usually we don't feel, we don't have that much exposure to deal with them in analytical perspective
Uh-huh.
to analyze the stable center, right?
Right.
So how did you analyze, apart from X-ray crystallography, which analytical techniques you utilize to identify which stable center is there?
Mm-hmm. Yeah, this is the NMR. Without NMR, the simple answer NMR. Okay. Without NMR, obviously, if you don't have X-ray structure, obviously, my supervisor is to say, ideally, organic chemists should not rely on X-ray. Before that, you are supposed to, if you are a good organic chemist, you are supposed to deduce the structure based on NMR data. That's what he used to suggest us. But what I'm trying to say is, all the stereochemistries were assigned based on NMR data. Okay. Once you, for example, you have SYN stereo centers, the respective protons, you can identify the coupling constant or the J value that you call. Based on that, you can assume or you can come to an estimation of whether they are syn or anti. Okay. So these are like the protons in see, these protons, right? So the cis and trans protons we talk about, right? All of you know that when you talk of J value, we all know that the trans has higher J value, cis has lower J value. Based on that, you can say. But once you are in a sp3 system, these things don't hold. Okay. Once you are in sp3 system, what I mean is, if at all you have something like this, for example, these are antiprotons, right? And the antiprotons, the J value is actually is reverse to what you have here. J value will be less here in the sp3 scenario versus the syn. Okay. So these things you have to be realizing before you are handling such compounds, and added to that the other data such as X-ray or whatsoever that helps you. And as such, you may be having some prior idea of your mechanism, right? When you are doing a reaction, for you probably it is new, but for me, I have some experience with this, so I know what can be the progress of the mechanism. Based on that also, I can have an idea what can be a preferred stereoisomer or whatever that is possible or not possible.
That's why I think it's very important that looking at your spending time on your data.
Yeah.
So nowadays what happening that you just spend, for example, initially you spend 600 to 700 rupees to get the spectrum, and you actually once you get one NMR, you just spend half hour, 1 hour on that. If I remember Dr. Hardwar, he is now still my supervisor. He used to have a box with like several pencils, eraser, sharpener, and then as soon as spectra comes, he swap. He would take the pen, sit, and then he'll keep on drawing all the possible structures, write down all the structures. So 1D NMR, and then we can go to 2D NMR and see
Yeah,
this
yeah, 2D. Of course, NMR I said, within NMR you have 1D, 2D NMR. 2D NMR is another very helpful technique. Yes.
Yeah, many times, many compounds, he said that they will struggle until they get crystal structure. So it is not possible that you just set up the crystallization and
Yeah,
do it next day.
yeah.
Sometimes it may take 6 months
Yeah,
to
true,
get
true, true.
crystal structure,
Yeah,
and
yeah.
we cannot sleep.
Organic
Okay,
chemists.
we cannot sleep if you have a structure data and you don't know. Sorry, you have data and you don't know the structure. So it is always goes around in your when you sleep also. So one
True,
day
true.
you get a dream. It is in front of you.
Yeah, true. I agree. Yeah. Because
And
especially organic compounds usually are not very much crystalline, usually, unless you are blessed.
So I think that is wonderful, and so thanks to Dr. Ramshastri for
Yeah.
including some data also.
Thank you.
Like it was a late
Yeah.
2 to 2 kilometers of data. But so what we are going to do, we have some around 10-15 slides with a few compounds and some data which we have recently recorded and wrote some paper.
Okay, so I think it has been a pleasure interacting with all of you in NIPER, and I just completed a little more than 10 years in Mohali, and so I don't really work on fluorinated compounds, but last 2 years we have ventured into some molecules which are fluorinated for certain reasons. We got into it, but without knowing much of the implication that would actually come in our way. But then it was a journey kind of unfolded for us, and I just wanted to show quickly the relevance why those fluorinated peptides or fluorinated polymers, they are relevant. So mostly you are looking at things from the medicinal chemistry perspective, but today I will give you in this talk, I will just give you a different glimpse or different flavor of how you can actually incorporate fluorine and get some interesting materials property out of it. That's very important. And so those of you who have not been to INST, so this is not very far at the moment. It was very across the road earlier, but it is now in sector 81. Okay, so you're most welcome to visit INST. So just to give you in 2 slides things why it is important for our work to incorporate fluorine. In our group, what we do is we actually look at nature and try to understand the underlying phenomena in nature that happens. Like nature typically, you have got a lot of non-covalent interaction that self-assemble the molecules to form certain structures, right? And based on the functional output of certain structures, you might also get some very interesting property. Like if you look into these top ones, like you have this bark of the tree, and it has its own wound healing mechanism by secretion of latex. Similarly, our body is also an example where you can actually have very nice wound healing, and you actually can also propel the wound healing to get faster if you provide certain patches like hydrogel patches or something like that. So our idea is that how we can actually develop, looking at nature, can we really make nature mimetic materials? If you look at bottom down there, we also actually work on precision structures. I mean, if you look at the honeycomb or the the ice crystals, what forms, and you want to make a lab, some nanoparticle or whatsoever you want to make, it's so difficult, right? There's a reason nature does it perfectly as a perfect engineer, which we in the lab often fail. The reason being is that the thermodynamic and kinetics of the process. Typically, nature does everything in an out of equilibrium process where things are all kinetically favored. But in the self-assembly, what we used to do earlier also, now also many of us do, they are all thermodynamically controlled. But that's where the things are quite different. Okay, so if you have to emulate nature mimetic property, you need to have out of equilibrium things, and we actually work in that directions. The last example which I am showing is something like muscle actuation. You see the chameleon, they change their color. And how do they change their color? And they are camouflage themselves from external attack. Look at our heart that is always pumping, right? These two have very unique property. Okay, so they have something like non-linear mechanical property. Okay, there's something called muscle actuation is happening. So we in India, we actually try to make such kind of materials synthetically and try to then look at the implication. Can you really use these materials for cell differentiation, for tissue formations, whether they actually match the natural material like biopolymers you get in nature, or you can do even better than that and they are processable or tailorable. So these are the objective we have in our group. So with that, we actually, we have a wonderful journey, and we start, that is where Professor GIAN's group and we interact quite often, is that we start with taking small peptides and try to look at if you take this peptide, design these peptides, using these non-covalent interaction like the amide hydrogen bonding or some additional interaction like pi-pi interaction, ionic interaction, can we now make those molecules self-assemble to form such kind of nanostructures, like it can be a nanofiber, it can be a nanoparticle, can we really control, and then from there can we really make a hierarchical structure, right? That's our job. And we started with this molecule, which was in 2018 ChemCom that came up, and you can see, okay, let me just get the pointer. Right. So you can see that it is an amyloid A beta 42 nucleating core inspired peptide. So you have V, then 2 phenylalanine, alanine, and then this side we put 2 lysine unit for better solubility. This side is your, your EPMOC group, so that it balances, and that actually gives you the self-assembly in water, and it forms very nice nanofibers we get to see. Over the time, this is just an introductory slide what we do for you. I will get to the flow. So then over the time what we did is that this N-terminus functionality, we also made it very nice stimuli responsive. We used Kumarin unit that can have this, very nice cycloaddition reaction reversible. We can open and close, and then accordingly we can change the, structure and the property of that. We also tried to make it redox responsive by putting a ferrocene onto it. The ferrocene can be done, can be oxidized into ferrocenium ion, and so it can change color. So we made very, very interesting conducting hydrogels, which are very important conducting hydrogels, because if you want to do neuronal tissue, tissue regeneration, you need to have certain conductivity into it. So some of the works which are under progress. Another interesting thing, this is where actually our fluoro things will start, is this azobenzene we put, and all of you know azobenzene can have very nice cis-trans isomerization, right? Incidentally, this is in trans form. If you shine UV light, 365 nanometer light, this will go into the cis form or Z form. And again, if you irradiate that with 405 visible light, it comes back into this. So we wanted to look at how are the self-assembly for this. Not only in N-terminus, over the time we also have looked at what happens if you change in the C-terminus. You can get catalytic amyloid-like property. You might get something very interesting, compartmentalization, co-acervation. You can have these very nice liquid-liquid droplet creations based on arginine, because arginine is very special. So we looked at all these different things. We have varied a lot of different things, and we try to look at this, and we make peptide is our basic building block. We self-assemble towards making hierarchical structure, which will be in the next slide. But this is where we ask a question, and we wanted to look at, this happens over a Gordon conference in Switzerland 2 years ago, in 2023 summer. When we went, I was wondering, and we came up with an Australian guy. We said that, okay, he can provide me something very nice, fluorinated azobenzene. Now, what happens in fluorinated azobenzene, which we'll eventually see, I just wanted to give you the hint. If you take fluorinated azobenzene, your trans to cis photoisomerization here we do in using visible light. You can actually do with the, here we do in the UV light. If you have fluorinated azobenzene, you can switch, you can make this photo switch, which is visible photo switch, which is very good, because if you have visible photo switch and you make hydrogel out of it, you don't need to shine UV light over your hydrogel, so that hydrogel will have a gel sol things over such harmful UV light. You can do it in visible light. That has an implication in photopharmacology. I have 2 slides to show why it is important later on. So this is another thing. This is the last slide from the general what we do in the group. You can see that we are actually inspired by this science paper, where it shows that if you make hydrogels, and if you actually take, your MSCs, mesenchymal stem cells, then what happens based on the hydrogel mechanical property? Every hydrogel will be some stiffer or something maybe weaker. You can see that your stem cells can get differentiated in the neuronal cells, or it can be in the, let's say, the muscle cells, or you can also get in the, the bone cells. You can get differentiated into it, which is very good if you want to make, let's say, extracellular matrix mimetic hydrogel scaffold material, which has a bigger implication in the regenerative medicine. That's what we do. And over here I showed this. You can make this peptide hydrogels. It's like a bone cement. We mineralize them, and this, you can see that they are self-healable. As I said, our body is wound healing, right? You cut it, it will automatically mend. These things are, you see, we cut this, then we mend it, and you see that they are color coded, and actually they fix. It's like a very nice glue, and we use this, and then we see that there is a very nice hydroxyapatite crystallization happens. That is very important, because your muscle and tendon, where your bone and the muscles are there, so you have these collagen fibers, And in the collagen fibers, you know that tropocollagens are there, and in tropocollagens you will have this hydroxyapatite crystallization which happens. We actually showed our synthetic material, which is peptides. Those peptides which I just showed, you can mineralize and you can generate such kind of things. Not only that, as I was saying, those heart kind of muscle cells, they always have this actuating behavior, and they show this kind of non-linear elastic behavior. Typically, you know, most of the material, hydrogel if you take, just tell me if you have seen any hydrogel. Morning when you wake up in the morning, right? So you get your toothpaste, right? You press the tube, that means you apply force, the hydrogel flows, and that's why it comes out from the tube. And once it comes out from the tube, you can put it on the brush and it does not flow anymore because you have removed the force, right? So this hydrogel is called shear thinning hydrogel. Typically most of the hydrogel, if you make any biomaterial you want to make, it will be like that. But if you have to really go for cardiac muscle cells, it has to have that actuating behavior. If such cardiac tissues or the, you know, our vein and arteries, if they have shear thinning like hydrogel, what would happen? During systole diastole movement, well, you cannot just withstand the pressure. It will fall and you will die, right? So for that, what you needed is that you needed strain stiffening. It should have a counterintuitive behavior that you put force, but this will resist. And then as a result of which, what will happen? You can see that at very low strain, the shear modulus increases. This is something very interesting, and this is something we are working in India. Only our group is working. And over the world, I think you will find hardly 7-8 groups who are working in. If you can make such synthetic material, they will be processable, tailorable, and you can actually change the entire ball game. And we have actually published something very recently. We are also filing patent for something. So you can make this peptide and you can join that with some polymer, and that also we are expert in polymer. So we can conjugate them well, and we can have injectable gels, and they can actually have very nice muscle cells proliferation. You can see we have actually looked at it also in animal studies and wound healing. It shows amazingly good behavior. So I am not going to show all this here. Just I wanted to give you briefly, this is our inspiration. Now what happens? These peptides, all the peptides, if you self-assemble, I will show that later, you have these amide bonds of peptide in their secondary structure. They orient themselves very nicely. You get a very nice secondary structure, right? You can follow it up by circular dichroism spectroscopy. But what happens is that because the amide bonds, their dipolar orientation makes it to have a very permanent polarization. If that happens, you can ideally generate something called piezoelectricity. And that has recently, it's over 5 years, there are a lot of hue and cry. It has given some field called peptide piezoelectronics. Okay. So this is something very interesting, and we thought perfect. And such kind of regenerative medicine, if you look at collagen, triple helix and all this, they have always this dipole pointing up. And if you now measure the piezoelectricity of collagen, they have also sizable, the piezoelectricity. And over the time you have seen that over the year, as you age, your bone get degraded, you see your piezo-responsive nature of the bone, that also changes. So there are a lot of work which is going on in that. So we can connect the piezoelectricity of the hydrogel scaffold along with this non-linear mechanical property to get a better regenerative materials. That is actually our goal. So what you need to do, you have to enhance the piezoelectricity. Perfect. Now, it is important so what I will show here, that if you actually have a fluorine incorporations, what you see is that you have this enhanced polarity and dipolar alignment because of the fluorine's high electronegativity. That is what you have learned. And you would also have this through space fluorine-fluorine interactions. I will show some of the data. And you will have this altered hydrophobicity. You have learnt about all these things. Now what would it have implication into it? First thing, and that is I am going to come, if you substitute fluorine on azobenzene, you see the fructoresponsive nature changes. It goes into visible range, which is very good. And you can have a very nice self-assembly control. So you can have self-assembly, something which was going slower because of the introduction of fluorine, your self-assembly may be faster. If self-assembly may be faster, your gelation kinetics might also change. That is very important. If you want to inject something quickly, like nowadays you are filling dental caries, right? You put a hydrogel. Ideally you put it and in 30 seconds it should fill, and then they will do UV curing, right? But if it takes, let's say, 5 minutes, so then you have to keep your mouth like jaw like this for 5 minutes. It's not painful, right? Small little things, they are very important. So we are looking at these things, and the last thing is the functional implication, that is the piezoelectric enhancement introducing fluorine. So these are very important thing. One is the piezoelectric enhancement, another thing is that getting into visible photo switch. So these are two aspects I will show in my next 10-15 minutes talk. And you can see typical azobenzene, if you look at, this is typical azobenzene. I was saying that from trans to cis, if you want to go, you have to do UV light, and this is the, you can reverse it using visible light, or you heat it up, then it comes back, right? And typically you see the UV visible spectra, it is like that. On the E azobenzene, you have this pi star transition. For that you get this particular band around 300 or so, and you get n pi star band, which is something like this, 450 is a peak. But what happens if you convert into Z, you see that pi star band goes down and your n pi star band comes up in this particular, the photo switch conversion. Okay, now importantly what I wanted to show here, here if you look at these n pi star excitation energies, they are very similar for both E and Z isomer. Okay, you can see that E and Z isomer in n pi star band, both in E and Z isomer, they are very similar. So that's why they tend to absorb in the same range. Okay, but if you now look at this particular molecule where you actually have this tetrafluoro1 molecule, we have now a variety of fluorinated. You can have tetrafluoro, we have got pentafluoro. We are trying to synthesize ourselves as well, not relying only on that Australian collaborator. So you can see that very interestingly, it can actually have switching into cis in green light. You can get it back using blue light. And the most interesting thing what I would like you to note is that because of this fluorine, which are actually adjacent, because of this electronegativity of fluorine, you can see that this actually gets stabilized, and because of that you see there is a difference between E and Z isomer. You see that there is a huge difference between n pi star transition here and n pi star transition over there, and because of that you can see that there are actually very different n pi star band you get. In this case normal azobenzene, you get the same kind of absorbance. In this particular case you have different one, and because it is different you can actually choose a tail wavelength where it is E, the blue one you see E. You can take 530 nanometer wavelength where there is no Z. You can use that wavelength to switch that from E form to Z form. You can use the tail wavelength in this, and that is why you can make this as visible photo switch, which is very good. Okay, and you can see over the you can see you can actually tune that in different molecule, this kind of EZ conversion using different kind of visible switch. So you can actually do a lot of different things. You can change their this optoelectronics property, which is very important for such azobenzene. Why it is important? It is important because this is something I don't need to really explain all the NIPA student. This is important because the drug has if you have the drug in the active form, it has this toxic level, right? And you also have you need to have concentration of the effective drug, which would actually this is something you are looking at, where you will have the efficacy. So people over the last 1 decade, I have been seeing the photopharmacology. Incidentally, when I was next to Ben Feringa's group, this William Szymanski, he was working with a good friend of mine. So they were working on in Ben Feringa's group. They were actually working on such kind of photopharmacology. The idea is the following: you take any drug, in that drug which is drug has an active site, and other than the active site, you might have certain site where you can actually put this photo switch. And what happens is that using this photo switch, like azobenzene as a photo switch, you can actually convert into cis and trans, and if you do so, you can actually you can make the drug prodrug or active drug. So this is something example. You can see that you can, based on this particular molecule, you can actually make it cis and trans, and you can make this drug active or inactive. And in fact you can see this, there is this example. There is another example where you can, there is an antibacterial drug. You can actually it is a normal azobenzene they have taken, and you can see that you can grow the bacteria, and one case you can mask it, and using light you can actually make one side potent antibacterial, another side bacterial growth still happens. So this is very important. That is one of the reasons we are working on such, the visible photo switch. And I showed you already an example why we are working on it. So now, what is the second objective, which is important for us, is the promoting piezoelectricity, and why fluorine is important. Now, if you have this, there are some inorganic piezoelectric material and barium titanate and all these things, they are inorganic. But you have to look for organic piezoelectric material. And one of the thing is this particular molecule called PVDF. And its PVDF actually can stay in 3 different conformation. Okay, it can be, you can see this is the fluorine atom. It can be alpha phase, beta phase and gamma phase. And you can see that in beta phase of the PVDF, they have very nice alignment. You see all the fluorines are at one side, orientation wise, right? Tacticity wise, if you look at, it will be like that. And because of that, there is a huge, because of fluorine electronegativity, there will be a dipole creation across, right? So, but in the gamma phase also you don't get such kind of things. And that is why you see this PVDF is very special. It will have a molecular structure. It will have a polar molecular structure which positively and negatively charged ends. You can have crystal phases. It can have alpha, beta, gamma, and the beta one is the most electroactive one and has the highest dipole moment because of its molecular structure, which is very essential for the piezoelectric values. And the last thing is that if you have this piezoelectric material and you can actually complete the circuit, right? So you can actually generate piezo response out of it. Now how do you do so? You can actually drop cast this piezoelectric material on some surface and you can actually connect it with a volt. Now you can do 2 things. One is that you can apply current, then you see that it will start giving a mechanical response, or if you tap on that particular material, you will see that there will be a current generation. That's what is piezoelectricity. Means I am waving my hand, and because I am waving the hand, it will generate current. So it will be intrinsic current which you will be generating. And how do you follow that up? You can actually see something like this butterfly loop. If you look at the amplitude of the mechanical force and the applied bias over here, you can actually have very nice butterfly loop like signature. It signifies that this material is piezo responsive. And you can actually quantify the D33 value, that is a coefficient of piezo response along this 33 plane. So you can quantify, and more you get the value, it's more piezo responsive. It's very important. And you can think of, piezo responsive is the sustainable future. You can put in your shoes such kind of material and you go for jogging and you can put your phone over here, you can get it charged. And that's what is already there. And in Netherlands, what they are coming up with, this is the road I am showing. Typically the cycle lane, what they have done is that they have put all this piezo responsive material, not organic piezoelectric, the inorganic one, they are putting, and as the car goes or cycle goes, they will get automatically charged, and the light, street light, will actually run based on that. So there's something very nice sustainable solution I just wanted to show. But then what is our gain is that in peptide piezoelectricity we wanted to do, because if you are making some hydrogel out of it, then that will have an implication in the regenerative medicine or extracellular matrix like thing. And this is an example I just picked up from advanced material. I'm sorry I didn't put it was so hurriedly made. I can share the slides, and you want something I can always share. This is an advanced material paper. You can see that this is very simple, CBZ peptide, single one. And in this particular one, you see that there is a 4th position, there is a fluorination. And you can look at the common structure over here. So they have done it. All are typical phenylalanine, or the 4th position para, they have phenylalanine, or all of them are phenylalanine. And when they have done it, and they have looked at from the crystal structure, I am not showing all in details, and you can actually put that very nicely over there, and then you can tap force. And if you tap force, you can actually generate piezoelectric response. And interestingly, you would appreciate that you see that this particular molecule, where you have only one fluorine, that has a very nice dipolar, one direction, right? But because if you have all throughout fluorine, then there will be a vector of the electronegativity that will cancel out to some extent. That's obvious. That's what this paper has proven. And you actually see that this guy shows the maximum piezoelectric response as compared to even the phenylalanine. In fact, the all pentafluoro, it has much lower one. Remember, this they have done it on a crystal. But I think we are also trying to put such kind of peptides in our material and trying to see how much in fiber, how much you can go because our aim is to go to regenerative medicines, right? And this example, it's got in advanced material, because you see Very interesting example. Typically, you go to Afghanistan, you will have all pista, badam, kaju badam, all these kind of things will come, right? It will all come. Now you have to sort them out. Machine learning, right? So they put it based, and your walnut, pista, kaju badam, all this, they will have a different shape and weight. Based on that, they are calibrated. If they put it on a weighing machine, which will be automatic sorter, then it will fall and it will give different response, and they will go in different sorting chain, and it will get sorted into kaju badam ke bottle mein kaju badam jayega, walnut ke bottle mein walnut ka bottle jayega. So it will be automated, and you can see that the piezo response in nanogenerator signal is actually quite different. So this is something interesting implication. Not only that, one can also, suppose you are not well, or you have got cough or cold, or you can do voice modulation because I'm talking. So you can put and you can do this mapping also. So there are a lot of interesting things piezo responsiveness can do, and already a lot of works are going on. I'm not getting there, but I wanted to show how we can do in the chemical perspective, or this particular one which we are doing. We did also this work. This was in Chem Matter in 2022, and you can see that this particular molecule, normal azobenzene, when we have put, and I can show it to you here. You see, this is a typical molecule, a monomer, and when you self-assemble them, you actually get it very nicely peptide self-assembly. Because of that, there is a remnant polarization over here, and that's why this molecule becomes piezo-responsive. But you disassemble this molecule, you don't get any polarization because it's all random directions. And that is very clear that when you have it in nanofiber form, you see very nice piezoelectric behavior. But in the case of all those molecules where you disassemble, you don't get to have such kind of behavior. You can again regenerate. This was the first example in literature. Before that, Gazit actually published some Nature and Science on this, but ours was a follow-up one, and we could show first time on-demand piezo response. In his case, he cannot do it. Whatever you get, you get. Okay. Having done that, we were now interested. That is actually the thing. Not only the visible photo switch. We thought that okay, the fluorine is there. Let us see what is the whether it has an effect. This is something we wanted to put it over here. We are also trying to put in this phenylalanine, such kind of fluoropeptides, just to see where you can manipulate that will have enhancement. So this is work in progress. So I cannot, it's going on. Just to show you couple of another example that how this the photo switching happens over here. As I said, even if you put these peptides into it, you can see that 3 to 300 band, it actually comes down when you do E2Z photoisomerization, and this N-pister band, it goes up. But interestingly, when you put this fluoroazobenzene over here, you can see that this is a very interesting. We did this DFT calculation, and this is what I had a very nice discussion with Ryan here. So you can see this fluoro, because of this ortho position, it will bump into it. So then it stays like this. You can see they are very interesting. It stays like this out of plane. Okay, and it folds back. And we can actually do this back and forth in monomer species. If you take on monomer of this, you can visible light, you can go, and then you can again come back. And you can nicely follow it up using the tail wavelength, which I just earlier showed. Even if you put it on peptide, it stays intact. Now the fun begins here. I will show you some NMR spectra to show. You see this. Interestingly, we showed, and I am giving you already the hint. This particular molecule, it forms very nice nanofibrous like structure. And if you shine light to cis form, actually you will see that there are this donut or medu vada like structure, and they are so stable it doesn't come back. This is something is very nice. This paper is now, it has gone for review. Now you can look at this molecule when we made it. We did a fluorine NMR, and you can look at this when we did this 19F fluorine NMR. So you have A type of fluorine, B type of fluorine, and C type of fluorine. 3 different type of fluorine, and you will get very nice 3 different peaks, right? And if you look at closely, like this is A peak which is coming, and the A peak has so many these things. Ideally, if you are talking about A peak, so you are getting coupling because of this fluorine, also, and also because of hydrogens, right? We learned this morning. This is a real case over here. So then what we did is that we did decoupled, proton decoupled we did, and then you can see that you get only the, the triplet because of the fluorine, because these are decoupled. Similarly, you can follow it up with the B over here. You can see it becomes doublet and the C over here. But now you might also ask me question that you are getting this which are major peak, but you are also getting little peak of this. What are they? Now this is interesting because when you have fluorinated azobenzene in the photostationary state, little bit of Z form will always be there, and that is why you are also getting this Z form peak. And we can calculate based on the integration how much E form is there, how much Z form is there. When you do photo switching, what happens to that? That I will show you. So it's very nice, and I'm also learning with you the fluorinated compounds and its NMR, and you can see that this was a E form, right? And E form had this kind of spectrum. More majorly, these are all due to E form, and these things are coming due to Z form because you can see that E form has around 87% of your molecule in the E form, right? And the rest are a little bit in the C form. You can actually calculate from both HPLC and NMR. We have corroborated that data. Now, if you shine light in 5-3, you can see that it goes into cis form, and as soon as you get into cis form, you can see that this peak becomes more, and this peak comes down, and this comes down, and this goes up. So you can see this very nice photo switching behavior between this molecule. We also, now this is very interesting, we also try to do POSI spectra, 2D.
How you did this experiment, NMR experiment? Like the light, how it was arranged, like this, how long it, or you just put the light and then turn the transmission?
Yeah.
Inside not possible, right?
We inside in situ we don't do. Basically you can see NMR is a quartz tube. So you can take two NMR, same one, you record it, shine light, again put it in, and they have, this is another interesting thing, I did not talk about it. When I was showing this UV spectra, the half-life of cis form in the fluorinated azobenzene is really good as compared to the visible light. This is something also very important, particularly if you are looking for the photopharmacology active form and dormant form, that perspective. This is important. So yeah, we do that way. And we also looked at the POSI, and you see that when you looked at in the E form, and this is the typical E form, the azobenzene, you can see the distance between the fluorine and the ipsocarbon is actually quite high, but if you go for the cis form, you see that drastically gets reduced. And because of this, you see that the 2D and POSI NMR, you see only the diagonal peaks, you don't get to have the cross peak. And we get to have only in the cis case, you get to have these cross peaks. They tend to interact over here. This is something very nice, and we found out, and thanks to Ryan and all the discussion this morning also with Srinivas, we now understand it's completely that what actually goes on. It's actually what happens is that this particular carbon becomes actually delta plus because of the fluorine it's pulling the electron, and this guy, okay, they can actually have very interesting stabilizing interaction over here. And not only that, it can also stabilize the other carbonyl atom of the peptide which are actually in the vicinity. Okay, I will come there when I show. Yeah, you can see that many of these things are actually closer. Many of the carbonyls are closer. So when it comes closer, you can see that there may be possible interaction, which we are going to look at through the DFT structure now. Anyway, now this is important to have the stabilizing interaction. Keep in mind. I just wanted to show you. So another interesting thing, because you put fluorinated azobenzene from normal azobenzene, you went from normal azobenzene to fluorinated azobenzene, you can follow it up by the circular dichroism. You can see that entire self-assembly from monomer to self-assembled structure like this kind of structure, it takes almost like 2 days to form. It really takes time. But if you put fluorinated azobenzene, incidentally it happens within maybe 4 or 5 hours. It just happens in 4 or 5 hours. So you can see that from 2 days, you can get your self-assembly to these nanofibers, which is an AFM image, you can get there so quickly. Now another interesting thing is that this guy, if you shine light 365, that is the UV part, you actually get into complete disassembly, that nanofiber-like structure. But in this particular case, as I was saying, you can see that there is this thing with a dot. It's all Medubara. Can you see that? So it's exactly like that. And incidentally, this, if you wait, it actually comes back. It never comes back. This is so stable, and that is why I was talking about the, the stabilizing interaction of the fluorine with the ipsocarbon and possible carbonyls. And that is what is stabilizing and it is folding back. It's like a hinge-like structure in the door. You can see the hinge in the door. I think it is something like that is happening, and it is not leaving it. So self-assembly, we saw comparative self-assembly, it gets really better and it gets stuck. And we followed it up. Of course, we followed it up by UV. I'm not going into details. Maybe you can see that this is the fiber we get. And we can do this photo switching very nicely. We can calculate from the UV or HPLC or NMR the percentage of photo switch. And you can see again from TEM. TEM, you can see that very nice such kind of Medora. Okay, actually our idea was and Gunjan has been doing this work, that can we make this Olympic ring, toroid, this we call toroids. We wanted to have this interconnected toroid. That was one of our goals. We tried, we have been still trying. Now we'll change the fluorine number of fluorine atom there, and we would like to make the Olympic ring, and it will be really fun, cool experiment, because there are one or two nature paper from Shiki Yagai's group in Japan, in Chiba University. He has been doing one or two, but not on peptides. He is doing on some pyromatic surface, not fluorinated also, but we are also going to get there. So with the fluorine in chemistry in mind. So I think I just showed it here, just one D NMR. When you have this nanofiber form, you don't get to see any peak because they get broadened. But as soon as you shine light and get such kind of structure from nanofiber to this, you get to see such kind of peaks actually emanates. That means there are certain amount of flexibility you get to create in the cis form. And we also did the dozy NMR, which we need to also repeat and do multiple times. We don't see much difference, but yeah, we see that in dozy, the self-assembled structure is actually a little higher than the, the Z one is a little higher, the toroid one is a little higher dozy as compared to this one.
So is it from amorphous to crystalline?
No, it is not amorphous to crystalline. Both are, both have certain amount of fibrous crystalline degree, but this to this, the morphology changes.
Nanoform, maybe it is
amorphous. Yeah, we have to do the sacks. It's a good point. We have to do the sacks, but sacks is not functional at the moment, I guess. So that's something we can definitely.
You're showing that cyclic form, but is it real cyclized or it is just because there is no any connection, right? Just the whole cycle.
Interestingly, if you start with, this is a very important crucial point, it depends on the history of the sample. So you take a Z form, put it in, throw them into water, they will form very nice fiber. Sorry, if you take a E form of the peptides, throw them into water, it will form very nice fiber. Now that E form you convert into Z form in the monomeric form and take that monomer, throw them into water, it will do nothing. But if you start from the fibers and then shine light, then it will form such kind of Medora. Okay, this is important. That means in the thing, in situ change is very important. That is what we are thinking, that maybe the adjacent fluorine is participating in the carbonyl. Some of these things we are trying to now validate with the MD, but I think I will show you a very nice MD simulation data. As I was saying, this is coming very closer, and you can see over here this is also coming very close to the carbonyl, which might have a participation of the neighboring intermolecular participation, and we actually looked at it. In MD simulation of E form, if you look at, you see very nice fiber-like formation you see. You get to have this 1D growth of the fiber. Our collaborator has done this. But as soon as you shine light, you introduce little bit of Z form into it, Z form, and you can see that you have this pore creation in between the fiber. That is actually, we cannot run more than 500 nanoseconds, the MD simulation, which is not possible. But I am pretty sure that if you can run it, you can actually eventually get into such kind of toroid-like structure, which is something very nice validation of our structure. And last thing, this is what we do always. We have not still tried the piezoelectricity of such fluorinated azotensin in the peptide, but we looked at our Kelvin probe. That is also similar thing. So what you do is that you take the AFM tip, touch the surface, and try to connect the circuit and see what is the surface potential of it. And in this particular case, in the cis form, you see that you have a very high surface potential, but in the case of trans, you have a very high cis form, you have a 664 volt around, but in the case of trans form, you have much lower, 84. So there is this structural orientation, it changes the, the electrical property. That is what we believe. The changes in piezoelectricity over this switching will be also quite dramatic. And that is why, and it will be also light responsive, visible light responsive. We can make hydrogels, and if you want to put some drug into the hydrogel and use some visible light, suppose you want to put it in colon, this is what we will be looking for. And you take a, the endoscopy thing and you put a localized thing, you put the visible light using without using any UV light, you can actually have a local release of the drug. So we have both piezoelectricity response that will go in a different way, but a visible photo switch will give us that particular tool to really get there. So I think I'll finish it here. So the introduction of fluorine, what we have learned from this, I don't know how long I took, 30 minutes or so. It makes the UV photo switch into visible photo switch, and the implication of photopharmacology and hydrogels, which I have been stressing on it, and we are working on that. Another thing is that it enhances the piezo response for actuating scaffold for tissue engineering scaffold, which we are also working towards that. And I think these are two important things, and that's what brings us the fluorine in, mysterious venture of, fluorine chemistry. And I would like to thank all my students. So I think this work is mostly triggered by Gunjan. You can probably find her here, and she's there also. And so she has done all this work in fluorinated azobenzene, and the other azobenzene work is being carried out by Jahanvi. So I think, they are working hard, and I'm able to present in front of you. And thank you for giving me this opportunity to share some of our recent updates using fluorine chemistry. Thank you.
Any questions? They're enjoying
This one? Yeah, we go every year in summer. I think we have a group retreat. We go some jungle and we do a group meeting there. We discuss science. So because we have to, what is our first life? We have to be nature mimicking. नेचर देखेंगे और उसको मिमिक करेंगे. So nature देख के wow बोलेंगे, उसके बाद subsequently we'll ask how. Wow and then how.
So regarding that cyclic structures, because you said that E form you put it in water, right? And then allow it first polymerization, and then you saw shine light. And then it cycled. So have you tried to work on the concentrations?
Yes. We have done that in different. Exactly. This is something we're trying to do all these kind of things. Yes, if it is a higher concentration, we also try to grow, put fibers into it so that it penetrates like this. Something like that, it stays. Then that will be like sikh kebab. Sikh kebab देखा? खाए हैं, right? सर लखनऊ से पता ही है. तो सीख कबाब में जैसे होता है कि you put things under the stick. We also wanted to put the nanofiber and put those rings, but we are struggling a little bit with this microscope. So some things we are asking is absolutely, and as I said that we wanted to make this catenine like rings, Olympic rings, or janjeer banana chahte hain. So those are some of the things we are looking at, and I believe that is only possible if you change a little bit in the peptide site, and also the number of fluorine if we change in the azobenzene. That is what we are now doing. So, of course, I did not show the synthesis. You don't get more than 20% yield when you actually make this fluorinated azobenzene. So what we start with is this difluoroaniline, then brominate over here. That bromine, you make I think we make it aniline, this side also, and then as diazotization and all this we do, and then get it something like that. Cyano becomes COH this side, and that aniline that we do diazotization to get it. But then you don't get good yield in the diazotization reaction, hardly 20%, but still, yeah. So we have a number of variety of system which is now coming up in the book. So let's see.
Any questions
from students? Are you masters or PhD?
It's long day. Masters, PhD, postdoc, yeah. So I think there are no questions. It was a very long and very nice, interesting day, and we should conclude with very thanks to Professor Ashish Pal. I request Professor Jain and also to join.
I think they are pioneer, and we are always getting inspired. Professor Bhattacharya and Professor Jain.
So what we are going to do, because we have only one day left, And we have two talks from Professor Altman, and he has very kindly agreed to, because one talk he planned for the Shiksha Mahakumbh, and that could not happen because of the very big event and lot of guests. So he will be giving a afternoon talk about his research. So it will be like a long lecture, long research talk, but we'll take a short break. Right, so 50 minutes too. So, and that lecture we will open it for all the institutes so that many other students also can join in the Friday afternoon. So I will also I will try to give you some by tonight. I will try to give you some some work for the fluid NMR. So some examples, some spectra, and then you need to try to work on those spectra and see if you can correlate the spectra with the structure. Okay, so this will be a kind of a spectral workshop what we are doing for the first year master students. And tomorrow we will have a biweekly function also. Those who have 100% attendance, only those will be given certificates. Yeah, or maybe 90%.
Yes.
Yeah. Okay, 80% because of the recommendation. So those who have more than 80% attendance, only those will get the certificate. The rest all will not give the certificates. Okay. So I think overall it was a very nice day. Let's conclude for today, and we will start our session tomorrow at 10 a.m. Okay.